participated in it. And these presentations really reflect the caliber of our students and the wonderful work that we're able to do under mentorship of our faculty. I want to give a special recognition first to the people who funded this program. As you know, money raised from this program is all from supporters of the DeMatteis School, and we typically spend about 100 to 120K every summer being able to provide stipend for the students. I also want to acknowledge the faculty mentors who during the summer worked with our students. This summer, for the first time, we even had few adjunct faculty. And again, both the dean's office and students are grateful for their mentorship, because without that, this process would have not been possible. So I personally looking forward to the presentation. I think Ms. Downey has communicated to everyone the protocol. She was working tirelessly this weekend to make sure this book is out. Unfortunately, due to some challenges with lack of cooperation with our staff, we are unable to live stream this today. But those of you who are in the room will definitely benefit from presentation. So Liz, each student has 10 minutes to present. Right. Right. Okay, so again, single presentations have total of 15 minutes, 10 to 12 for presentation, 3 minutes for Q&A. When the presentation is a group of 2 or so, that time increases to 20 minutes. So again, they have approximately 15 to 16 minutes for the presentation, and then 3 to 4 minutes for Q&A. Again, faculty mentors, if you want to introduce your students when they come up, feel free to do so, and also make sure to keep track of the time by using hand motion or anything you see fit to make sure we stay on time. So let's start with our first presentation. I'm really looking forward to this presentation, and the first presentation by Matthew, who worked under tutelage of Professor Lane, one of our own graduates who's currently at adjunct faculty. Matthew.
Hello everyone, I'm ASPiRe. My mentor is Professor Lane, and I worked on the investigation of deep learning for effective computing, music-based emotion recognition research. So very quickly, I'm going to try and make sure I get through everything as fast as possible, because this might take about 11 minutes. So intro to effective computing, this was founded in 1995 by Rosalind Pickard, which she defines the term as study and development of systems and devices that we recognize, interpret, process, and simulate human affects and different emotions. Okay, so music therapy, there were 2 relevant interventions in music therapy, either receptive and interactive intervention. These are beneficial for facilitating memory or reminiscence, developing auditory skills, visual anxiety, etc. However, one meta-analysis showed that receptive intervention was more effective than interactive intervention, specifically for young children and for older adult patients. This was actually found that the setup involved in interactive intervention actually complicated the effectiveness of the process. So some motivation. I then looked into current things on effective computing with music therapy, and I found MindTrack, a brain-computer interface, which synthesized brainwave data, including emotion, and converted it into one instrument movement, which would affect the key signature and tempo of that song. So it's relatively simple. The intersection of these 2 disciplines led me to be curious to see what particular aspects of emotion can be learned in order to identify with emotion, and later on, would it be possible to transfer the mood of music in a particular song while retaining as much of the original content possible. Now you might be thinking, well, why do this when you can just choose a different song in therapy? Well, for the interactive intervention of therapy, it is useful as it can help express emotions with higher quality music than just playing a random instrument. And it can also help the patient more quickly evaluate what changes in the song, since the only changes could be related to emotion. So with this, the idea that I could potentially help improve some people's lives and do some research in infectious disease, I found my motivation. So very quickly, again, it's part of deep learning, which is inside of artificial, there's an umbrella term known as machine learning, which is anything that has to do with learning from past experience. Deep learning in particular, in machine learning involving neural networks with intermediate layers in those neural networks that help the learning progressively higher to other people. The transition didn't work. So the generator in a GAN is essentially generating some sort of data from a data set and replicate it. The discriminator's job is to differentiate between the real data it's looking at and the fake data from the generator. And over time, you learn better and better, so the generator makes data just like the real data set. So this is my process. I'll get into that right now. So choosing data. Eventually, I moved into moving data as I found about music therapy. Then Professor Lane told me about the surface light model, which brought up the shedding light on the idea that I would need to be having some sort of consistent scale when identifying emotions. So that led me to eventually find Spotify's metadata, which actually has valence and energy as values that they've determined for every song. I then went on to pre-process this particular data. What I did was I chose playlists that were happy and sad instrumental data. I then further made sure I was getting happy and sad songs by choosing corresponding high and low valence songs based on the metadata. Here I then went on to plot the particular data. I had found some interesting insights that happy music was more danceable, more energetic, louder, and found to be more often in the second mode. I then moved on to scaling the data and removing any songs outside of 3 standard deviations for any of the values to normalize it, which then moved on to my exploratory data analysis, which I further then moved on to find principal components in my principal component analysis, which I found, as I noticed in the plot, the mode and acousticness seem to be the most important when dealing with instrumental music. Now, I then went on to perform clean clusters to identify grouping. After fixing my graph, I realized that the sadder songs tended to have negative values for the second principal component, showing some sort of trend between happy and sad instrumentation. I then went on to compare it with a different genre of rock music, and I found different principal components in these, but also the trends were not as clear, at least from what I could tell on this graph. So that led to some insights that maybe different genres have different trends in respect to effective data. Okay, so moving into my model, I have been trying to look at using raw audio, which is also available to be accessed from Spotify's API. However, I've then found that MIDI files were good. One particular model was CycleGAN, so this is building off of the idea of a GAN. Just quickly, that was the generator, and that one's the discriminator in the regular GAN. But here's the CycleGAN. So as opposed to a GAN, which can learn I like one domain of data, CycleGAN can learn 2 domains of data, meaning happy and sad. So here we can see it would, this model would be taking domain data of A, or happy, would then convert it to sad, or generate it from sad, and then convert it back to happy. This cycle occurs the same way, other way around, from sad, happy, sad. Now, the loss function, that cycle consists of loss, and then there's also our loss functions based on the results of the discriminator. In a way, you can kind of think of those as loss functions that are like checks and balances to ensure region quality and retain as much of the original content as possible. So some pros and cons. In this particular model, I had found that it worked with MIDI files. So now originally I wanted the raw audio, but MIDI files are kind of like sheet music, so it's the data per file size is relatively smaller, so it's easier to work with. Unfortunately, though, this model was relatively old, so it was very hard to just get this particular model running with all the dependencies, as well as I couldn't just instantly import the trained model. I would have to train it myself, which took a lot of time. And one other con is that while I had done an analysis on Spotify metadata to help find trends in happening set, I was unsure how to identify emotions in MIDI files. So, moving on to a different model compared to the cyclogen. So you might be wondering, well, there's other generative models. What's so special about a cyclogen? Or maybe you might even be thinking, well, I know long short-term memory models are good for time series data. So as long as time series, why not use that? Well, while cyclograms do have part of the residual neural networks of LSTMs, this does have longer term learning capability. However, the particular data set this cyclogram was trained on had the music set to 16 time steps per bar, so that is very persistent time frame of music. And the data, well, besides the point, the cyclogram is able to have cycle consistency loss, whereas the long-term short-term memory model does not, which means this will verify it's retaining as much of the original song as possible, whereas this model would just learn better patterns of music. So some results. I'm going to show this at the end, but I had originally wanted to get into some intermediate results and final results and some other results about things. But at the end, I'll just show. I'll play on my phone and just speakers final results of the cyclogram. It's just showing the genre transfer, which is what the original version of that cyclogram was meant to do. Just to show a proof of concept that if I have repurposed the data, I could actually make effective transfer of music. So some tips and tools. Metadata supplied by Spotify can help you bring useful insights for effective computing, as I shown by performing my EDA experiment. The key difference between raw audio and MIDI files. MIDI files is more like sheet music, but on a comparison to file size, it's more lightweight. Raw audio is more complex, so you probably learn more complex aspects of music on the side. Metadata for classification of emotion and using MIDI files for generation is probably the best direction, and this would likely be done on a site again. So, some motivations for future works. I could, if I wanted to, I could collaborate with the Department of Psychology in order to get effective labeling data from participants. But there's no metadata in these MIDI files that I have as close to Spotify music. Determining a metric would be important. One particular route that could be done for this is taking all the title names in the given data set of MIDI files, looking up if those songs are in Spotify, and then actually being able to pull the respective metadata to then classify it by emotion, so then you can put it into the cyclogram model based on what's happening with that, as opposed to original purpose, which was classic for that. Some other options for future work. This model is relatively old, so refactoring it for training would likely also yield better results, and expanding the model later on to be able to take in multiple MIDI files would also be useful for improvement. So, I'm going to get into, I'll play, the first example is the genre in jazz, and then it's going to be classic. So this is the jazz version. And this is the singing component in classic. So you can see that some of the key and tempo has been retained while changing a little bit of the music. But yes, unfortunately, I wasn't able to perform that for effective transfer because I didn't have a proper data set as I originally planned. Now, feature may be unclear, but it's up to you to choose how you sing the song. So that was a lot. I know it's written. There's a lot more in between, metaphorical gaps between bullet point and slide, but I'm free to open to any questions or concerns, and thank you for your time. this is focusing on domain transfer changing from like happy to ever generation just in general is more common in areas such as that. Yes, right. Yeah, that is possible. However, one thing that I do know is implementing artificial intelligence within cybersecurity is becoming more common. So maybe something that on like social media platforms to detect things that could potentially be manipulative like that could be like that's the common challenge. Yes. Right. Yeah. So I looked into that. I found two things. One thing is that this first started with a different company called DeMatteis that bought out Spotify then bought out. Essentially, they had started off in 2016 by first having specialists come in and listen to the songs and label the data, and then use machine learning to extend those results upon many other songs. They also then took into account people using crowdsourced data, identifying those values, and then some sort of like synthesis combination of those is what ultimately they did. Any other questions? Yeah, it was pretty convenient. There's a thing for Spotify for developers where you can sign up pretty much anyone can. You're able to pull, aside from just audio features, you can also pull audio analysis and 30-second audio samples every time. Copyright. Yeah, yeah. Yeah. Right, right. Yeah, so that's something that can be done in programs, and especially if you're able to get this effective commercially. Any other questions? All right, well, thank you for your time.
Well, if you could kindly close your presentation when you're done, and then the next group, your presentation is loaded here. Just click on it. They're all in order.
Hi, good morning. My name is Daniel Rivas, and I'm a bioengineering senior student. And I present about ultrasonic isolation of particles derived from channel with strong chemical reactions with the embodiment of processing and order. For the background, I'm not familiar with the term, particles is fast material, and it's also known as multiple structure, which are able to differentiate a lot of processes. For example, bone cells, skin cells, liver cells, um, because would say using it in parallel, so there's a lot of relation and the how we do it. So methods we use like PPT indicator notifications. We use that very second cycle, meaning that the sample will be connected for 30 seconds and you will write for we use that a lot for all the data that we do over at the use the sample system here and sometimes we want to compare the sample that we did were pretty clear and for the finding of the ratio of the mean and the fat and also using the PG experiment and all that and calculation make that temperature in the password and part of the temperature. These are the laboratory experiments that you can see over that at the calories and organically vary with the number of repeats for that cycle. On the left side you can see the overall experience that they're preparing. Assuming the topic is the chemical research that we do. You can see on the right here, you can see the case of the research. In this case, this is a correlated research. You can see the capillary fold here. And that is what we found out is that the reuse that you want that was both brain and it was not able to use the quantity cells that we use with the correlated one. It is another accelerated temperature was able to propagate the differences in all color relations because of the code that were consecutively between the laminars and therefore communicating with the whole inside of the research instead of the new color of the new temperature which only communicated the sample that was really on the right, on the bottom right, you can see the ranking of the sample temperature before and after the presentation procedure. Which makes sense that there was not a highlight to the temperature that after I committed the test with the right for each symptom. For example, you can do like 3 repetitions of 30 cycles to do the most viable cells, while there's a chart right afterwards for the 5 or 6 repetitions. You look at the presentation and you have your liver cells. In conclusion, and explain the results. And for future research, we try to
Stephon Warwood, also mechanical engineer, going into my senior year. Our project focused on self-corrected buckling in helical structures with Andy Warren.
So, spring buckling is a very old question that has been thoroughly studied. The first thorough study was done in 1949 in Paris. He developed a lot of the buckling load. However, this model basically had contact between the coils, which usually occurs at smaller scale. So that becomes a lot more relevant today as we use micro and nano-scale coil springs. See all the contact between the coils. And so this project is studying the effect that contact between the coils can have.
And so, as we were saying, the project focused on specifically finding a region where that did not occur. So instead of straight compression or straight buckling, we were looking for the phenomena you'll see in this video, which we are referring to as corrected buckling. The spring will continue to be compressed, it'll begin to deflect, and then the coils, as they hit each other, will come back and resemble no compression, or just straight compression. And here we just have the three possible behaviors that we saw in our study. So all the way on the left, no buckling, which is what you would expect from a typical spring, just being completely compressed, straight. Corrected buckling, which was our focus in finding where this happened in certain springs by divvying up the lengths. Deflected, and then came back to no buckling. And as we saw in the first video, uncorrected buckling, where the deflection continues to come out in the spring.
So, for our experimental setup, in order to test a variety of lengths of springs, in the previous slide, the only difference between those different behaviors was the compression length that we were using in between our lathe chuck jaws. So the method that we came up with for testing these springs was we needed a way to grip the springs so that they wouldn't, when in compression, they wouldn't buckle out and fall out of their mount. So we came up with using lathe chucks, as you can see in this picture here. We would mount the spring, one end of the spring, into a lathe chuck, and we would have the same setup inverted from the top. We were using the Instron compression machine in the engineering materials laboratory, and so we needed there was no way for us to attach the chucks right off the bat. We had to develop a mount, as you can see here, and we did that with the help of Mr. McKenzie. And so that just helps adapt the mounting mechanism for the lathe chucks to the existing machine mount. So in order to automate the compression test, the software that the machine uses is called Blue Hill. And in there, you're able to create programs that allow you to automate the process. So that allows us to just input parameters that we need to set for the test, and then we can just hit start, and then we'll run the test itself. And that makes it easier to run multiple tests. And so we tested a range of springs, range in diameter from 2.9 millimeters to 31.24 millimeters, and diameter of the wire was from 3.6 millimeters to 3.68.
We also have problems with the spring slipping inside of the jaws. So we implemented, as you can see, there's like a little bolt or shim there. And this prevented the spring from slipping and messing up our results. So for our experimental procedure, we use Herring's buckling formula, as you can see below. It's the delta critical over L naught. And we solved this equation for L naught over D, and we came up with a value of 5.242. And when L naught over D is less than this value, we experience no buckling. And when it's greater than this value, we see buckling. And this is helpful for when we are cutting lengths of the spring, because we only had a certain amount of spring we could cut. So we wanted to make sure that we had enough length of spring to see all of the phenomena that we were testing. So you could see here where L1 is, it's equal to the 5.242 times D, minus the 2 inches we took into account for safety factors, and then plus another 6 inches, which is 3 inches inside of each chuck portion of the chuck. So we could just see the buckling phenomena. This L value is when we see straight buckling, and we work down from there and see corrected buckling as we go down, and eventually just no buckling and just straight compression.
And so these are our experimental results. As we said, we tested a range of springs, being very tiny, of up to like 0.2 millimeters all the way to 32 millimeters. And the blue line here is Herring's original model, which only accounted for straight compression and then any type of buckling. And as you can see with these initial results going from blue to any of the other colors, it follows it pretty accurately, except for a few outliers as we continue to get larger. On the y-axis is a non-dimensionalized radius, and on the x-axis is our non-dimensionalized compression ratio. This is just the compressed length over the full length when we did compress it, and for rho, that is the radius over the uncompressed length. We non-dimensionalize these terms so that this can be applied to all springs for future research, and so other people could use this if they wanted to continue this type of research as well.
So for Herring's buckling model, the reason it's a straight line across and not kind of fit to the data we have is his model only took into account the non-dimensionalized radius. It did not take into account the compression ratio, so that's why it's just a straight line across. But his original model was used to predict the region or the transition point between no buckling and uncorrected buckling. Where our study differs is we were trying to find that in-between region of corrected buckling, which is not documented yet. So the way that we developed our or originally, the way that Herring's developed his model was he based the center line of his spring, or the springs that he was working on, and he based them on a beam. So he was able to use the constitutive equations for buckling in a beam and apply them to springs at the larger scale because he observed that the behavior between them was similar. So these two equations there are the constitutive buckling equations for beams, which we classically study in engineering 28 strength of materials.
And then as you could see below, we have the no contact case, edge contact case, and full contact case. The no contact case is, like Jeffrey said, we use the equations from a beam, and these are just the regular constitutive equations. And then the edge contact is the new formula that we developed with Professor Borum, and it takes into account contact between the coils and the equation seen below. And then full contact is when there's maximal compression and no bending, and there's those equations seen. So
this is Herring's original buckling formula, which predicts the critical deflection at which buckling occurs. So how far you have to compress it before you get this buckling. And so as you can see, that term on the left is the non-dimensionalized critical deflection, and this term relies on the diameter of the spring and the original length and true curvature.
Below this equation is an equation used for buckling of beams, and this equation has been defined for a long time. And when we equate these two equations, we can solve for C, which is the spring stiffness ratio, and this will give a decent approximation for us where we can see the region between buckling and corrected buckling, which we'll see in a later graph how well that line was fitted with our data.
So the reason we're able to equate these terms, these equations, is due to the fact that beam behavior and spring behavior in buckling was similar as Harring's observed. So we were able to find C, which is the spring stiffness ratio, by setting these terms equal. We were given the diameter and the length, and we were able to isolate C. So what you're looking at here is the model that our professor, Professor Borum, developed in MATLAB. So what this is he took the center line, which we used to model after the beam, and he, in order to take into account the coils, he added in these rungs laterally to account for the coils. And he put a constraint on it that they weren't allowed to pass through each other, which was something that Harring's model did not take into account. I guess at the scale he was working at, he didn't have to worry about that issue. So we had to implement that constraint. So the way this model works is it runs different simulations for different lengths, and it takes note of the behavior, either full compression, corrected buckling, or uncorrected buckling, and it marks that, or it stores that data, and using that, the model he developed was fit to that data.
So as you can see here, this is the graph we saw before. Now on top of the graph, we plotted the predicted corrected boundary, which is when we equated those two equations, and we fit a line to it. And as you can see, it isn't the best approximation. It does a decent job of approximating the region, but we think with further experiments using more variety of springs, that we will be able to get this region zoned in a little bit better than we have. And as you can see now, where Harring's model only took into account the non-dimensional coil radius, our model takes into account the coil radius as well as the compression ratio here.
So in conclusion, our model is able to determine the three qualitative behaviors observed in the experiment: total compression, corrected buckling, uncorrected buckling. And although there are quantitative discrepancies between the experimental and predicted results, as Luke was saying, with more variety of springs and more tests, we believe we can fine-tune that region where corrected buckling occurs. We're currently exploring the source of these discrepancies, particularly in revisiting the original model that Harring's used, and future work would also consider other contact-dependent phenomena in the coil springs at the desktop scale, nanoscale, and microscale. And before we finish out and accept questions, we did want to give an honorable mention to one of the other projects that we attempted to work on this summer, and we'll go into a little bit about that.
So the purpose of this project, the study of the mechanics of the musical saw, is to observe how harmonic excitation affects the behavior of flexible structures. So what you can see here is a saw that is mounted in, on one side, we built a mount to the table. On the other side, it's held in one of the other Instron machines, and it's used to create this shape, which in our study, when you develop this S shape in a flexible structure and you excite it with some method, our method chosen here is using a musical bow. And so the friction between the hairs and the blade of the saw developed vibrations, and that was the sound you were hearing. And so, yeah, some future work, one of the problems we ran into this was that we weren't able to reproduce the sounds at each point as we were hearing. Yeah, there was a lack of consistency, so we had to put this project on hold for now. But we hope to, in further work, to use electromagnetic excitation, which should give us a more repeatable result.
Help us out throughout the semester. We might be able to produce more consistent results.
And one last thing. We did also want to thank Dr. McKenzie, Mr. McKenzie, Andy Borum, and everyone else who helped us with this research. We are now open for questions.
Yeah, I think so. I think it did have somewhat of an effect, but we kept it consistent on how fast we were compressing them. I think it was at a rate of 0.2 millimeters per second. So that data that we showed was just for that specific rate. But I mean, it could possibly have an effect. We just haven't really seen a different range of speed, so we're not too sure on how that would affect it. Right. Right, so the upper bound is already defined. So that's Herring's formula. And so that has already been studied before, and it does a decent estimate of determining the range at which, the region at which it switches from no buckling to corrected buckling. The red line, which you see, is what we try to develop and try to fit to where the region differs from corrected buckling to uncorrected buckling, which hasn't been done. A little, right, yeah, we want to get that a little bit right. Yep.
I'd say that our results, the reason that it doesn't completely follow hand in hand, because there's probably human error in the ways that the experiment probably could be better. But Herring's is very well defined, and that's why we took that design.
I think he derived that equation from the original beam formulas, and so that accounted for Young's modulus. And yeah, I'm pretty sure it had to do with that, but I know Professor Bowen would know a lot better because he equated those two equations for us and solved them. So if you want to reach out to him and ask him, I'm sure he would do that.
Yeah, I mean, it's included here in the spring stiffness ratio, which he used to develop his model. Yeah, that was why we solved for C, so that he used that in his simulations to develop it. The second equation is just for general beam behavior in Bartlett. So we used that and equated these two equations since they're both set equal to the critical deflection. We were able to set them equal to each other. We were given this, or we had that data of the diameter and the length. And we were able to solve for C, which includes I believe it's the modulus, the axial force, and the moment of inertia of the spring. And I think that yield stress would be more along the lines of the actual material of the wire and where that would stand, whereas in the model it's kind of more taking into account the spring as a whole structure, which doesn't, where it differs from a beam is where a beam would snap at a certain point, a spring just deflects out. It might be something to look into further in our model.
Hello everyone, my name is and I'm a rising senior majoring in computer science. This past summer I worked alongside Dr. Owen Segal and Dr. Barak Abikan of Hofstra Northwell in researching machine learning-based predictive models in the service of in vitro fertilization. So for some background, IVF is an assisted reproductive procedure that's generally used in cases of infertility or genetic defect. And outlined in the slides is a full IVF cycle, step by step, which can be categorized into 7 main stages, starting with blood work and ultrasound, where patient data is collected, ovarian hyperstimulation, where a follicle-stimulating hormone is injected into the patient in order to increase egg production. Then the eggs are triggered into their last stage of maturation, and later are retrieved, where the metaphase 2 or mature eggs are isolated, and those eggs are then fertilized in a lab, and the healthiest looking embryos are then transferred back into the patient. After about a 2-week break, the patient is given a pregnancy test to determine whether or not the process was successful. Results in an IVF cycle generally vary pretty significantly based on several variables. Specifically, the higher the mature egg production, the greater the chance of a successful cycle are. Multiple cycles are sometimes necessary, and IVF is not a risk-free procedure, so during egg retrieval, patients are prone to risks such as injury or infection, and prior to this, doctors face a decision-making process to determine whether the conditions are stable enough for the pregnancy to occur, and if not, they might cancel the cycle. So this is kind of where our research fits in. Our goal is to assist with this decision-making process by increasing the predictability of IVF cycle outcomes, and what we're trying to predict is the total production of mature eggs produced. And we can do this using machine learning. So machine learning models search for patterns algorithmically when given a data set to train itself on. And after training, it can then make predictions on new samples of data. So in this data set, we're working with 4 features. Unfortunately, half the data points had more features, but we couldn't use them since most of the data had missing values. So the features we're working with are the estrogen level, which is measured on trigger day, then the number of follicles greater than 14 milliliters found on the ovaries recorded via ultrasound, and this was found to be our best predictor, which makes sense considering each follicle can produce a single mature egg. Then we have the anti-Müllerian hormone levels, which is also a good predictor, and the patient age. And the outcome variable is the number of mature eggs retrieved. So the overall workflow went as follows. Our partners over at Northwell Health collected data, and this is an ongoing process. They're still extracting more features and getting more data points so we can continue to improve our models. And then once we receive them on our side, I wrote a script to parse, clean, and format the data. This had to be pretty thorough because a lot of data was written in plain text and coded in a certain way, so it needed to be translated so the models can read them properly. And then we explore the data for trends, and based off of these trends, we selected which features to continue within our model and train our model with. After training, we evaluated the results, and the best model was then deployed on our web application, which is just a simple web form to be used by gynecologists in IVF. So here's the correlation matrix that we use for data exploration that shows the correlation between all of the features with the outcome. What's important here is the last column, and the highest correlation with the outcome variable, as mentioned before, the number of follicles greater than 14 milliliters at 0.67, which generally implies that it can serve as a good predictor. The other variables, like participant age, are generally a little bit lower, but we continued with all these features in the model since they all improve performance. So in terms of how we tackled this particular problem, we trained our models to solve 2 different problems. The first was a regression problem, where we just predict the exact number of mature eggs to be retrieved. And the second was a classification problem, where there are 2 possible outcomes. The first is negative, where there are greater than or equal to 3 mature eggs extracted. And the second is the positive outcome, where there are less than 3 mature eggs extracted. And 3 was chosen as the breakpoint because generally in a cycle, if there are less than 3 mature eggs expected to be retrieved, the cycle will be canceled. And so if you're looking at the number of data points for each outcome, you notice there's a pretty large disparity. And for training a classification model, especially with this data set, which isn't particularly easily differentiable, it was pretty problematic because the models would generally just predict the majority class 99.9% of the time. So in order to solve this problem, we used a synthetic minority oversampling technique, which balances the outcome count by creating synthetic data by connecting lines between data points in the minority class and adding points along those lines. Now, in terms of the models that were best for actually both problems, we used the feed-forward neural network architecture pictured on the right of the slide, where the top is basically the input layer where the features are inputted into those 4 neurons, which go into the hidden layer, which are fed formula from the previous layer's neurons, and the weights, which are adjusted during training. The final layer, the output layer, represents the 2 possible outcomes, and the probabilities of each outcome is what the final output is, and you just take the higher of the 2 probabilities to determine the model's prediction. So to evaluate the classification model, we can use a confusion matrix, where each box tells us the number of predictions that are true negative, false positive, false negative, and true positive. And we included the model without oversampling and with oversampling to show you why it's necessary. So if you look at the model on the left, you can see that it has a higher accuracy, or much higher accuracy than the model on the right. But if you look at the way it makes its predictions, only once does it ever predict positive, and it misses 31 out of 32 positive cases. And this is pretty unacceptable for a problem like this. So what's the most important statistic here is the recall, which is basically the rate at which the model recognizes positive cases, where the model on the right performs much better. The drawback is there are many more false positives due to this, and the false positive percentage is pretty high. But in generally with medical problems, you'd rather have false positives than false negatives. And for the regression, we can graph the predicted values along with the actual values. Here, the x-axis is just an arbitrary continuous variable we chose estrogen, but just to differentiate the points. The y-axis is the outcome, and the gap between the blue and the vertical gap between the blue and red dots represents the error. So on average, the predictions were off by about 3.07 mature eggs, and the standard deviation between the errors was 4.33. And if you look at the graph, you can notice that it's a pretty linear trend in the way that the model is making its predictions, and also the way that the data is spread. And the fluctuation is just due to the other features that were used in the model that aren't shown here. But you can also notice that the general trend of the data, just at least with this feature, is a little bit unpredictable. So in conclusion, we did run into some limitations with the data set we were working with. The number of data points, we had about 2,000 total data points, but we're still in the process of continuing or collecting more. And also the potential features, such as the follicle stimulating hormone dosage and the body mass index of the patient. These were included in some of the data points, but most of the data points did not have these features, unfortunately. And during testing, we did find that these features pretty greatly improved model performance. Overall, these models, really, they shouldn't be the end-all be-all. There were definitely some flaws with them, but they do provide good insight based on the previous data, and they should be used to assist the final decision. I included this here, 15-second clip of just how the web app that we built is to be used. It's just a form hosted on Amazon Web Services, and it'll give you the prediction after entering data. So I'm open to questions, and thank you to Dr. Segal for mentoring me throughout the summer. most of the time, the procedures would actually be continued. The data that we collected was pretty much, it wasn't really like, we didn't take specific patients or whatnot, whatever the case, it was just, that would be the actual, like, general ratio that the outcome of, well, also actually, to be specific, the data was collected after the procedure already happened. So those, like if we go back to the classification, you can see the total data points. These positive data points, those procedures weren't canceled actually. They continued with them, but if they had known what the outcome was in advance, then they would be canceled. Yeah. Yeah, so one of the ideas that we did have initially, and this could be probably part of future work, is extracting maybe the reasoning for the IVF procedure, whether it's infertility or any other potential reasons to go with the procedure. That probably does have some weight onto why an IVF procedure may or may not fail. I mean, what we could have, I guess, maybe done is raise this break point so that that there would be more data samples within this gap, but we want to be as accurate as possible as to when the cycles would generally be canceled. But aside from that, I don't really think there was much off the top of my head. Thank you guys.
We had a little technical difficulties. They uploaded their new presentation a few minutes ago, and this was preloaded this morning. Is it, it's similar but slightly different, and they can let me know if they need to. Okay.
Hello. My name's Chris Barbera. This is Matt Hansen, and this is our project experimental investigation of vortex shedding patterns of tapered cylinder pairs. And our faculty advisors were Dr. David Mooney and Dr. John Vaccaro. So these are the contents of our presentation. We have our background information, experimental apparatus, our measurement techniques, some of our results, future work, and our conclusions that we came to. So some background information: flow over a cylinder creates predictable vortex shedding patterns, and this vortex shedding frequency can be characterized by the Struhel number, which is basically just a non-dimensional frequency. And Struhel number, as you can see, equals frequency times the mean diameter of the cylinder over the free stream velocity. And two other variables to be aware of are the aspect ratio, which is the length divided by the mean diameter of the cylinder, and the taper ratio, which is the length divided by the base diameter minus the tip diameter. And this picture on the right here represents the three types of vortex structures. The first one being the tip vortex structure, which and this occurs due to the flow going over the free end of the cylinder. The second one is the Carmen, and this is the particular vortex formation that we're going to be concerned with for our presentation. And the third one is the horseshoe vortex, which occurs, and this occurs due to the boundary layer. This is the geometry for our cylinder pair. P is the distance between the center of the two cylinders, and alpha is the angle of the oncoming flow and the cylinder pairs. When alpha equals 0 degrees, the downstream cylinder is directly behind the upstream cylinder, and when alpha equals 90 degrees, they're side by side each other. And these are our 4 cylinders that we tested. All of them are 152.4 millimeters, which is the same as 6 inches. The first 3 cylinders are tapered cylinders, and the fourth one is a non-tapered cylinder, which means that it has a constant diameter throughout its length. And the taper ratios vary from 96 to 48, and the aspect ratios vary from 68 to 24. And for our presentation, we're just going to be concerned with cylinder 3 and cylinder 4. And this is a picture of our test section setup. Those are the 2 cylinders in pair, and behind that is the hot wire anemometer, which measures the airspeed of the vortices. And hot wire is 3 mean diameters behind the back cylinder and 1 mean diameter over. This picture on the right is a front view of our test section, and this is taken from the front of the wind tunnel. And that fan in the back is the fan that controls the airspeed of the wind tunnel. This is the same picture, just with the upper plate on top of the 2 cylinders, and we designed this upper plate to eliminate the tip vortex structures. I'm going to let Matt take over from here.
Okay, so this is a sample spectral analysis result for a single tapered cylinder at Z over L equals 0.5. So on the left is just a diagram of how we define the position of the probe. L is the total length of the probe, and Z over L just represents the height of the probe divided by the total length. On the right, we have a sample spectral density result. Here we see that the frequency peaks at 500 hertz, so that's the main frequency, and this corresponds to a non-dimensionalized Struhel number of 0.24. So this is our result for a solitary straight cylinder with a with a free end. So we see that it has a Struhel number of 0.1. Oh, I'm sorry, I should explain this first. So the example data on the previous slide was the spectra at one particular height. To fully understand the flow behind the cylinder, data was collected at 59 points along the span. And then these spectra were superposed on this 3-dimensional plot. So it allows us to understand the shedding frequency along the length of the cylinder. So for this particular case, we found a Struhel number of 0.19, and we see that we have very clearly defined peaks in the middle, And towards the top of the cylinder, that peak kind of rounds off. So we see Z over L on the y-axis there, and that represents the height of the cylinder. So 1 on the left is the tip of the cylinder, and 0 on the right is the base of the cylinder. So now with the same cylinder, the single straight cylinder, when we add a top plate, so that clear acrylic plate that goes on the top, we see that the screw hole number decreases from 0.19 to 0.15. And we also see at the tip on the left there, we get a clear signal, and that's because the upper plate prevents flow over the tip and it preserves the Karman vortex shedding. We also see a harmonic of the main shedding frequency at screw hole number of 0.3. Okay, so now we are looking at a single tapered cylinder, again with a free end. So now, because of the changing diameter of the cylinder, we see that the screw hole number varies from 0.15 to about 0.26. And we can also see 4 distinct shedding cells. And that represents the different cell structures due to the change in diameter. So now when we add the top plate to the single tapered cylinder, we see, much like the untapered cylinder, that the screw hole number shifts to the left. So now the screw hole number starts at about 0.1 at the base and goes to 0.15. And again, we see the peaks are much clearer from the base to the peak of the tip of the cylinder. So this is a diagram of wake interference patterns in relation to transverse and streamwise separation. The y-axis represents the horizontal distance between the cylinders, and the x-axis represents the forward and backward separation of the cylinders. Along the y-axis, they're side by side, and on the x-axis, they are in line with each other. The separation is measured in terms of mean diameter, and we conducted all our tests at either a separation of around 2 or 4 mean diameters. This diagram is only for straight cylinders, but we're using it to understand what would happen if they were tapered. So due to the changing diameter, the relative spacing changes from the base to the tip. So due to the wider base, for example, so now looking at a straight cylinder pair, with the angle between them of 0, and they are spaced 2 mean diameters apart. We see that it has a screw hole number of 0.15, which is less than the one of the cylinders by itself, which, if you remember, was 0.19. And this is because the cylinders are close enough that they act as one single object, so their effective mean diameter is greater, and that causes the screw hole number to decrease. So now, looking at the same 2 straight cylinders when they're spaced 4 mean diameters apart, we see again that we have a lower screw hole number of 0.14, and we also observed very strong harmonics of the main shedding frequency. Now looking at the tapered cylinder pair in line with each other and at a separation of 2 mean diameters, we see the changing screw hole number again, this time from about 0.1 to 0.16. So similar to the pair of straight cylinders, this combination produces lower screw hole numbers when compared to the individual tapered cylinders. And we did not observe many clear shedding cells in this case. Now, looking at the same tapered cylinders in line with each other, but this time spaced 4 mean diameters apart, we did observe shedding cells. So you can see 1, 2, and 3 cells right there. Now, when we change the angle to 30 degrees, now we're looking at the straight cylinders again, again spaced 2 mean diameters apart. We see that we see one distinct peak at a Strouhal number of 0.1, and then similar to when these were in line with each other, they have a larger effective diameter. However, in this configuration, they produce an even lower Strouhal number. So looking at the straight cylinders, again at angle 30 degrees, but now spaced further apart. We again see a Strouhal number of 0.1. However, this peak is less clearly defined. And interestingly, there does not seem to be a change in frequency at this angle when we adjust the spacing. So now looking at the tapered cylinders at 30 degrees and with the spacing of 2 mean diameters, we see the main shedding frequency starts at 0.7 and increases to 0.14 at the tip. And we can also see 3 main vortex shedding cells. Interestingly, the peaks on the right reverse the trend we've observed so far for tapered cylinders. So they actually have a lower frequency at the tip and at the base. And this change is due to flow between the cylinders, what we call gap flow. And this smaller gap towards the base of the cylinder increases the velocity of the air when compared to the wider separation at the tip of the cylinder due to the decreasing diameter. And so this increase in airspeed creates higher frequency vortices. So again, looking at the tapered cylinder pair, this time at 30 degrees with a in larger spacing. So again, we see that reverse trend with the left branch. If it's a Y, that left branch, again with the lower frequency at the tip and higher frequency at the base, is again due to the gap flow. And the right branch represents the main vortex shedding frequencies that we've been observing. And we see three shedding cells there. Interestingly, we see a third peak showing a consistent shedding frequency along the entire span of the tapered cylinder. You can see that there at Strouhal number 0.2. And we hypothesize that this is that this consistent Strouhal number peak is due to an interaction of the gap and main shedding vortices. And so now for our conclusion, we found that a finite cylinder with a free end generates higher vortex shedding frequencies than the same cylinder with an attached flat plate at the upper end for both straight cylinders and tapered cylinders. This upper plate the upper plate inhibits tip vortex structures and widens the downstream wake, producing lower frequencies than in the absence of the tip flow. Now, cellular span-wise vortex shedding patterns exist, and for tapered cylinders, even with a free end and moderate aspect ratios, although a fixed upper end plate produces narrow power spectral density peaks and diminishes the span-wise spread of frequencies. And lastly, tapered cylinder pairs produce wake interference patterns that are more complex than the straight cylinder pairs, and this is because the relative spacing of the cylinders increases with span-wise position as local diameter decreases. And for our future work, we'd like to shift focus to very high aspect ratio models with an aspect ratio over 200. And this will minimize end effects on span-wise shedding. So we won't see that roll-off that we observed towards the tip of the cylinder. And we'd like to conduct a thorough investigation of upper end plate effects on span-wise vortex shedding patterns behind the tapered cylinders. And here are our references. If there's any questions? Okay, so I'm sure you guys are very eager for an encore. For our second presentation, we are looking at the effects of spacing on a close coupled delta wing pair. Again, my name is Matt. This is Chris. Our research advisors were Dr. Rooney and Dr. Vaquero. And on the right here, we see an image of a Saab 39 fighter jet. And this is what is considered a delta wing. And this forward wing, upstream wing, is called a canard. And this canard assists with maneuverability of the fighter jet. So in this presentation, we would like to go over the background behind the experiment, our motivations and goals, review of some previous work, going over our experimental setup, our preliminary results, and then our future work, as well as our conclusions. So delta wings, which are down here, are triangular in their shape, and they have very sharp leading edges. And these leading edge vortices is what actually produces lift for the wing. And delta wings also have to be optimized for trisonic flight, which means that they operate in the subsonic, transonic, and supersonic ranges. In a tandem configuration, which is what we are particularly interested in, there is an upstream and a downstream wing. And these two wings in tandem can actually improve performance. Our motivation behind this research is to investigate vortex interaction. So we want to investigate the interaction between the vortices of the upstream and downstream wing to further improve aircraft maneuverability, as well as generally optimizing the flight characteristics of the aircraft. And our goal is we'd like to ascertain angles, find specific angles of attack for peak performance, and understand the manner in which air flows over the closely coupled wings. Specifically, we want to utilize the vortices generated by the canard to strengthen the leading edge vortex of the downstream wing. So previous studies have shown that vortices that form off of highly swept canards induce suction on the upper surface of the downstream wing. That the addition of the canard can delay flow separation from the downstream wing, which is desirable, and respectively facilitating lift and delaying stall characteristics. Research, however, has also indicated that the flow off of an upstream wing can create vortices below the downstream wing that negatively affect performance. We used an Aerolab open circuit subsonic wind tunnel. Our test section was 24 by 12 by 12. We conducted our tests at a speed of 45 meters per second. And to collect data, we used an ATI gamma load cell. So it's capable of measuring forces in X, Y, and Z, as well as moments in X, Y, and Z. And that was placed on the other side of this plate on the downstream wing. And using the forces that we record, we can correlate to that to lift and drag coefficients, which is what we'll be looking at. So this is our setup. We can see here the upstream and the downstream wing. The upstream wing has a sweep angle of 60 degrees, quite aggressive, and then the downstream wing has a sweep angle of 30 degrees. We vary the spacing at either 0, 1/4, 1/2, or 1 chord length apart. And that chord length is the chord length of the upstream wing, and the chord length is just the distance between the leading edge and the trailing edge. And finally, we varied the angle of the upstream and downstream wing. The upstream wing angle we called alpha, and this was varied from -15 to +50 degrees. And the downstream wing angle we refer to as beta, and that was varied from 0 to 50 degrees as well. And Chris is going to look at our results.
Okay, so this page, this is the baseline plots This is just when the wing is by itself, just one wing. We varied the angle of attack from 0 to 50 degrees. The plot on the top left is lift coefficient versus the angle of attack. This plot is the drag coefficient versus the angle of attack, and the one in the middle is aerodynamic efficiency versus the angle of attack. And aerodynamic efficiency is just the coefficient of lift divided by the coefficient of drag. And in the lift coefficient plot, we can see that the stall angle occurs at 20 degrees, and the stall angle is where the maximum coefficient of lift occurs, and after that angle, the coefficient of lift gradually decreases. And in the drag versus angle of attack plot, we can see that as we increase the angle of attack from 0 to 50 degrees, the drag increases as well. And now we're going to look at some effects of spacing on the lift coefficient. So this plot is the lift coefficient versus the downstream angle of attack beta for an upstream angle of negative 10 degrees. And we varied the downstream angle of attack from 0 to 50 degrees. The 4 red lines represent the 4 different spacings when they're right next to each other, which is when there's no spacing between them, when they're a quarter chord length apart, when they're a half chord length apart, and when they're a full chord length apart. And the white line is, again, the baseline, which is just when it's just one wing by itself. And this plot was particularly interesting because the closest spacing when they're right next to each other has the same stall angle as the baseline, but for the other 3 spacings, the stall angle decreases to negative 15 degrees. So now this is for when the upstream angle is at 0 degrees. And for all 4 cases, the stall angle occurs at 20 degrees, which again is the same stall angle as the baseline. And the pre-stall characteristics are quite similar. Once we get to the post-stall characteristics, that's where they start to kind of deviate. The closest spacing has a soft stall, which means that the coefficient of lift gradually decreases. For the other 3 spacings, they have a more severe stall, but that stall is still better than the baseline stall, which is the white line, which is quite severe. And now this is for when the upstream wing is at an angle of attack of 10 degrees. And this plot shows that the closest spacing when the 2 wings are right next to each other has a stall of 30 degrees, stall angle of 30 degrees. And for the other 3 spacings, they have a stall angle of 25 degrees. And again, the baseline stall has a stall angle of 20 degrees. This plot is for when the upstream angle of attack is at 30 degrees. And this plot was particularly interesting because our farthest spacing actually produced the best coefficient of lift. And as we decreased the spacing, that coefficient of lift got less and less. And that bottom line with the bottom blue line with the triangles, that's our closest spacing. Now we're going to look at aerodynamic efficiency versus our downstream angle of attack for an upstream angle of 0 degrees. And for our first 3 cases, when the 2 wings are right next to each other, when they're a quarter chord length apart, and when they're a half chord length apart, their aerodynamic efficiencies are quite similar. But as you increase the spacing to 1 chord length, the aerodynamic efficiency goes way up. And as you can see, it's actually quite similar to the baseline aerodynamic efficiency. And now this is for when the upstream angle of attack is at 15 degrees. And this is the only case we had where we actually had a higher aerodynamic efficiency than the baseline. But this only occurred for when the 2 wings are right next to each other. Now we're going to look at the lift coefficient versus the downstream angle of attack for all of our upstream angles. So from negative 15 to 50. And we varied the downstream angle of attack from 0 to 50 degrees. And the plot on the left is when the 2 wings are closest to each other, and then the plot on the right is when the 2 wings are farthest apart from each other. And these 2 plots indicate that as you increase the spacing, the spread gets tighter and tighter, which indicates that the upstream wing had less importance on the downstream wing as you increase increase the spacing. Also, we observed that as you increase the angle of attack of the upstream wing, the stall angle increases, but the coefficient of lift decreases. And this is true for both cases. And now this is our drag coefficient versus the downstream angle of attack for all the upstream angles. And we can see that it's quite similar to our coefficients of lift, where as the plot on the left is when they're closest to each other, and the plot on the right is when they're farthest away. And we can see that as it gets farther and farther away, the spread gets tighter and tighter, which again indicates that the upstream wing has less importance. The downstream wing has that spacing increases. So in conclusion, we came up with, in general, increasing the upstream wing angle of attack increases the stall angle and decreases the lift coefficient and the drag coefficient. Also, the relative spacing between the wings leads to different downstream wing stall characteristics. In the future, we would like to use the particle image velocimetry, which will allow us to actually visualize the interactions between the two wings as we change the angles. And then also, in the future, we would like to vary the vertical positions of the two wings. Here's our reference. Any questions? Okay. Thank you guys for your time.
developing a method for chromatographic separation of hair. Is it completely off? Okay, sorry. So this summer I've been working on developing a method for chromatographic separation of hair biomolecules. So in tissue engineering and regenerative medicine, there is a need for materials with good biocompatibility and bioengineering properties for use as scaffolds for cell reproduction. So these protein hydrogels are important because they act as a temporary cellular matrix and they allow the growth of cells, they allow growth factors and cell signaling molecules, and hair fiber protein extracts are currently used as gel-able materials, but these are still unemployable for clinical use due to their heterogeneous composition and their uncharacterized composition. So I have a diagram here of a hair fiber. The outer part of the hair fiber is referred to as the cuticle. Inside the cuticle is the cortex. Moving further in, we have the matrix where we have a lot of our keratin-associated proteins. So keratin-associated proteins I'm going to be referring to as caps for the rest of the presentation, just to keep it a little shorter. And those caps are all connected with disulfide bonds, and they surround keratin type 1 and type 2 in the most inward part of the hair fiber. So some students in our lab were actually able to extract total proteins from hair fibers. So the hair fibers on the left were delipidized, and then they were treated with a variety of reducing agents. These reducing agents were able to open the cortex and extract total proteins from the center of the hair, and it left us with this soluble solution, which has evidence of keratins and caps in it. They characterize that with SDS stage. So the caps and keratins are characterized by molecular weight. On the right, I just have a diagram showing keratins as the red rods, and caps as the blue spheres, and as you can see, they all have free thiol groups. So these free thiol groups tend to interact and create disulfide bonds with each other. So because of that, one of three things can happen. Sometimes we have keratins forming bonds with other keratins. We sometimes have keratins forming bonds with caps, caps forming bonds with caps. So this tends to be an issue with liquid chromatography, because the proteins, first of all, we're trying to purify them, and they're all interacting, clumping together, making bigger and larger proteins. They're also very dependent on the reagents that they're in and the pH of the solution, whether or not they're in this state, that state, or kind of going back and forth. So what we had done to help this was we capped it with iodoacetamide. So iodoacetamide is a capping agent that interacts with the disulfide bonds in the protein, and it basically caps it so that those free thiol groups are no longer creating disulfide bonds with each other, and it allows you to have keratins capped with IAA, capped with IAA, and they're not interacting with each other. So objectives, we were working on developing a purification method to separate keratin proteins and caps from hair fiber extracts using various liquid chromatography methods. Specifically, we looked at size exclusion chromatography and hydrophobic interaction chromatography. So what is liquid chromatography? Liquid chromatography is a technique used to separate and purify soluble proteins based on their properties. So the machine on the right is actually up in the cell and tissue engineering lab. That is the ASPiRe 25L system. It's from Cytiva, which was formerly known as GE Healthcare. And then this machine is connected to the ASPiRe. This is a fraction collector. The fraction collector actually allows you to collect designated amounts from your flow through from the machine. So you can set it to collect like 3 milliliters, and what it will do is it will collect the 3 milliliters in one of the tubes, and then it will turn and collect the next 3 milliliters in another tube. And that allows you to actually, characterize and look at these proteins in the area of the run that you want to see them. So one of the first methods that we worked on was size exclusion chromatography. So size exclusion chromatography takes advantage of the different molecular weights of proteins. So for size exclusion chromatography, there is media inside of our column. The media has all of these little channels that basically create a maze for the proteins. So the larger proteins tend to just flow right through the media, whereas the medium and smaller ones tend to actually make their way through these channels, through the mazes, which takes them longer to come out of the column. So the graph on the right here is the absorbance. It's showing absorbance, so it's UV reading, which is directly correlated with the protein concentration. As you can see, the higher molecular weight molecules come out first because they are not going through the channels. The medium ones are going through the channels, taking them longer to come out of the column, and our low molecular weights are going through even more intricate channels, and they are coming out of the column later on. So this is one of our chromatograms when we actually injected the sample that we earlier capped with iodoacetamide. As you can see, there were about 6 peaks, and they are separated peaks, which did suggest that the proteins did come out at different points as we had expected. We did collect these fractions in the fraction collector, and we ran them in SDSPage. So you can see the hair extracts over there, which was before we injected anything into the machine. That has some signals around the 40 to 60 kilodalton range, which is where we would expect to find keratins. And there were also some signals around the 12 to 25 kilodalton range, around where we would expect to see the caps, the keratin-associated proteins. We characterized our actual fractions, and on peaks 2 and peaks 3, we had some markings around the keratin range, as well as around the caps range. But when you move on to peaks number 5 and peaks number 6, I kept this up here so you can see which peaks those were. You'll notice that there's only marks around the range for caps, which suggests that we were at least able to purify caps. Peak number 6 even has even smaller caps in there, so we were able to kind of separate the caps in size exclusion. So then we continued on to look at hydrophobic interaction chromatography. Hydrophobic interaction chromatography takes advantage of the different hydrophobicities of proteins. So keratins, when they're in very high salt concentrations, are very hydrophobic. So we put our sample in a high salt concentration. It was about 2 molar ammonium chloride. And we injected this into the machine. So the keratins and the caps become hydrophobic, and they will interact and stick inside the columns. And then what you do is you apply a decreasing salt concentration, and the decreasing salt concentration causes the protein to elute at different time periods as they are becoming less and less hydrophobic. So in this way, we're separating our proteins based on their hydrophobicity. So we did do a run of hydrophobic interaction chromatography. You can see the flow through I labeled over there. This purple line is an absorbance reading again, so it's directly correlated with the concentration of proteins in our sample. So our flow through, those are molecules that did not interact with the column at all, they just flowed through. And then we had a peak number 1, a peak number 2, and a peak number 3. And the yellow line is our conductivity, so that's the number of charged particles. So where the yellow line starts to go down, that is where we started to decrease the salt concentration. So we also collected those fractions and we ran them in SDSPage. Again, the sample before injection, you can see keratins type 1 and type 2 had signals around the molecular weight we would expect to find keratins. We also had signals around the same molecular weight we'd expect to find some of the caps. Our flow through, on the other hand, this time only had markings for caps, which suggested that the caps did not interact with the column, they just simply flowed through. Peak number 2, you can see a mark around the 60 kilodalton range, and then peak number 3, there is a faint mark around the about like 40-ish kilodalton range, which suggested that we were able to separate keratins from the samples, but possibly different types of keratins based on them having different molecular weight. So then, because there was a large amount of flow through, we did increase the salt concentration. So this was another run where the main difference was we increased from 2 molar ammonium chloride to 3 molar ammonium chloride. We still had a very large flow through, and then we had peaks number 1, 2, and 3 in very similar locations as before. So we did collect and characterize these with SDSPage once again, and you can see again there were some signals in the 40 to 60 kilodalton range around where we'd expect to find keratins, Also some signals in like the 12 to 25 kilodalton range where we'd expect to find caps. Our flow through, once again, had signals around the caps range only, suggesting that the caps might be flowing right through the column. And then peaks 2 and 3, we had some marks in the keratin range. Again, they were at slightly different areas, which suggests that there might be different types of keratin that eluted at different points as we were decreasing the salt concentration. So in conclusion, we were able to purify proteins indicative of caps and keratin. In the future, we do want to continue to work to upscale this method to increase the yield. We want to continue to confirm repeatability. And when we collect enough samples, we want to make gels for use in tissue engineering. As well, we're hoping to verify identities of the proteins via mass spectrometry. Thank you. Any questions? So we still have to actually measure that. We haven't done that yet, but we can use the chromatogram and the known previous concentration in order to figure that out. That's one of our future goals as well. I definitely think so, yes. That would be something to look into using. Yeah, I've used it in the past, but I haven't used it on these fractions yet, so it'd be cool to look into. Definitely more than what we're currently getting. It's very low concentration, and we're only using a 1 milliliter column. So we want to order and make our own much larger columns so that we can get a higher concentration for sure. And we've been like concentrating the samples as well with evaporation. So, any other questions? Yeah, so we've actually done some protein assays to measure the concentration already. I didn't include that in here, but I can't quite remember the book, but we have done it a couple times to characterize them. Oh, so these are around the 40 to 60 kilodalton, and these are around 12 to 25 for the caps. And then the protein ladder is on the left for that one. Any other questions?
Hi, my name is Ashley Marquez, and today I'll be presenting my research on microfluidic devices. To start, blood vessels are usually modeled by using 2D monolayer of endothelial cells, and although this is very convenient, it is not very accurate representation of how they function in the body because they do not mimic natural structures. And because of that, they change the cell morphology and cause change in genetic expressions. And due to the change from in vivo to in vitro, they also have dysfunctions in their regular cell functions, such as differentiation, proliferation, response to stimuli, and other cell functions. Though, on the other hand, organoids are much better models because they are 3D multicellular structures that are self-organized. And since they're able to mimic the architecture and physiology of an organ, they make for better, more robust models. But the challenge with organoids is that they're unable to grow after a certain size or complexity because they lack vasculature and at some point develop a necrotic core. And because they don't have vasculature, certain areas in the organoid, they don't receive enough nutrients nor are able to relieve themselves of metabolic waste. And current technology being developed like organ-on-a-chip create cellular microenvironments that are able to culture miniature tissues inside of them by controlling the microenvironment in order to maintain the tissue-specific functionalities of the cell. But the main problem with organ-on-a-chip devices is that they still culture their cells on a monolayer. If you look in the image on the bottom, you can see that although there are multiple cell types, they're still on a single layer, which is not true to the natural structure of the lung. So although this is a flawed system, it provides the platform to be able to culture organs in a method that is specific to them. And with this on-a-chip technology, we hope to apply it to organoids in order to culture them with ease. And to then, if you're able to vascularize them, it would increase the longevity of these organoids. And of course, increase them in complexity and size and the functionality overall. So the objective of our project was to create a microfluidic device. The objective of our project was to create a vascularized construct in vitro. And to do this, we would first create our own PDMS-based microfluidic device, which would then be seeded with cells in a 3D scaffold using fibrin. And creating a pressure gradient would help them self-organize into these capillaries, which we would then test with fluorescent beads and heparinized blood to test the stability of the vessel. And then we would connect it to a pump to see how laminar shear stress would affect it after a long period of time. And here's an image on the bottom of how the pressure gradient is made by putting media on syringes. So you have an idea of when I start explaining the setup that this is the pressure gradient we're talking about. So to start, we would first have to design our molds on AutoCAD. Various molds were designed that required different densities, different volumes, and some of them even have runways to create more laminar flow. On the side over here, there are two molds that we designed so the first one is only a chamber of 800 microns, and the second one is a 400 micron chamber, but it has a runway for laminar flow. And on the bottom is an IBD device, which is a commercially available device, but it's a commercially available device that's made of plastic that we use as our control. And so once we design these molds, we printed them on a resin 3D printer, which uses liquid resin that uses a laser to cure liquid resin into plastic. And the benefits of it is that it created a smooth surface and would also and the material itself is also very heat resistant, which is important because we would cure the PDMS at a high temperature. And so the reason why we chose PDMS specifically was because of the exchanges of gas that happen. And that's very important in cell culture because we need to keep a concentration of gases at all times. But also other reasonings for PDMS is that it's optically transparent, biocompatible, and adheres well to rocks. The device itself was made by first mixing in a 1:10 ratio of curing agent to polymer base. We mixed it, degassed it, and then poured it into the mold. These were then cured at 80 degrees Celsius for 1 hour and 40 minutes. And the timing was really important because we could not fully cure the polymer, or else it wouldn't adhere properly to the glass slide. So we had to make sure it was cured enough that it would sustain its shape, but not too cured that it wouldn't adhere to the glass slide. After it's somewhat cured, we took them out, disinfected them with isopropyl alcohol and ethanol, and prepared them for plasma treatment. Now, plasma treatment helps create bonds between the glass slide and the PDMS, but it also helps with the cell adhesion within the chamber to make sure that cells adhere properly to the surfaces. After the device was assembled, we put under UV sterilization before use overnight so it can kill off any remaining bacteria. To load cells onto these devices, you first suspend cells into the fibrinogen solution. Ramen is quickly added to the solution, and we aspirate it and inject it into the device, as you can see on the top image right there. This is then let to solidify for 15 minutes, and after that time has passed, we then create a pressure gradient by collecting the 2 syringes as you saw before with 1 ml of media on 1 syringe. And then we would keep this pressure gradient for 3 days by recycling the media in order to make sure that they vascularize correctly. After 3 days, we would connect them to the pump, as you can see how we connect the device on the bottom, and we would examine how continual laminar shear stress would affect the vessels. In our first result slide, we have 2 images, one of an IBD device and the other one of our PDMS-based device. And we stained them specifically with stains that were specifically endothelial cell markers. So the red is for DeMatteis, the green is for CD31, and the blue is for closest nuclear dye. And just so you can get a closer image of the dyes, as you can see on the edges over here is the DeMatteis to show the interaction between cells, and the green is just the cell, the inside the cell. And so these images are just meant to show the quality of imaging between our devices and the IBD devices that are commercially available. And of course, ours has a higher quality because of the glass cover slip that we use on the bottom. It's very thin, and the material is of course transparent, so it provides for clear imaging, unlike the IBD, which is made of plastic and has a really thick slide on the bottom. And the second image right here is a tile image of the entire chamber, so you can see the complexity of the entire network and how it just spans from the inlet to the outlet. And if you take a closer look, there we have a nice really dense area of vessels. Just and you can see how everything is interconnected with one another. And just so when we measure these vessels as well, the average vessel density was between 25 to 30 microns, and it was bigger than normal vessels in the body, because vessels in the body are usually 10 microns in diameter. And over here we have a 3D rendition of an area inside the device. And this is meant to show that this is just a random geometry organization. We had no control over the geometry of the device and nothing, because everything was super random. And so no device is similar in its geometry. And this just shows how it just spans between the entire device and all the height. But you just can't see the rest of it because the working distance of the microscope isn't able to capture the entire 800 micron height. And right here is when we tested our capillaries by flowing fluorescent beads through the capillaries. Using 1 micron fluorescent beads that are red, we flow them through just to check if there's any leakage between the vessels. We want to make sure that there are tight junctions between cells. And as you can see, there's nothing outside the capillary, which is outlined in green, which is the CD31. But the red dots are all inside. And here's when we flowed heparinized blood to the capillaries. And this was meant to see, because if it vascularized correctly, it should not be clotted. And if it plays, then maybe I can show you what's not. Sorry, the video does not work. But the result of this test was that there was no visible clotting within the capillaries, showing that it vascularized correctly. And here on our last stage of the experiment is when we connected the vessels to a pump. And we wanted to see how flow rate would affect the vessel diameter or the vessel density. And so here in the static flow, as I mentioned before, vessels average between 25 to 30 microns. So when we flowed media at a 50 microliter per minute rate, we we saw an increase in diameter of between 35 and 40 microns. But the conclusions are, but we can't make any definitive conclusions because we don't have no data for this. In conclusion, we were able to create mechanically fit stable vessels in our PDMS-based devices, but we still need to test the effects of long-term shear stresses on our vessels, and meaning in the future we would have to optimize our system to be able to reach lower flow rates. But we hope that using biomechanical forces we'll be able to create more stable, physiological, and durable vessels. Acknowledgement, I'd like to thank my mentor, Dr. Ravani, Dr. Myrna in his lab, and German, and the purchase and attending for all the help making devices. And that's the presentation. So usually we would seed only, so the way we seed right now is using the EC cells with the fibrinogen, and we just inject it into the device, but later on we hope to inject spheroids of different organs, of different cells types, so that they vascularize with the ECs in the device. What colors? Oh, the molds? So when we cure the polymer, then these become holes, and these are the inlets where we can flow liquid through them. This is the, so we can have multiple chambers to view, with multiple vessel numbers. But if you look, use the diagram, it's how it looks like. Yes, they can be used to vascularize organs. Organoids are just organs that are made in the lab from stem cells. And the problem usually is because they're not vascularized, that they don't survive long enough. So any sort of tissue can be implanted into them. This is just meant to help vascularize the tissue to make sure that they are able to survive longer than what they're used to without vascularization. No, it's heparinized blood. It's heparinized blood. We push heparinized blood. Yes, actually, we ran into a lot of problems with the pump. Usually, whenever I try to implant, put in the inlets on the side, the air from like the pump itself would break the vessels. But but we're trying to optimize the system so that I can be able to attach the inlets before even attaching the pump, so that I can just use lower locks for the syringes and it won't cause much air bubbles or damages to the vessels. It's still a work in process. We're still optimizing the pump right now. Do we? I'm not actually sure. We were given blood. We currently go at 50 microliters per minute, but that's actually really fast for the vessels. We're trying to go below 1 right now, but we're trying to find the right pump, the right settings for it. Yes. But that's the point of the test for us to see if there's something outside, there's not anything in it. I mean, the image that I'm showing you right now is the top layer, which is the layer on the glass slide, which is the most beautiful. No, we have a fibrin scaffold holding these cells. I think they become more stable actually because the particular calculators are made of those two cell types. So it just reinforces the maintenance of the cells and hopefully make them more physiological.
Hello. My name is Vivian I, and this summer I worked with Professor Gary on monitoring a system for an autonomous robot wound closure system. So to give a brief background on the system, this is a robotic autonomous wound closure system, and it's designed to robotically conduct various surgical and other medical procedure without a trained professional to operate it. So so as you can see here, this utilizes programmable magnetic fixtures to close wounds. And some of the benefit of this is like it promotes healing and it minimizes infection and reduces scarring. So to give a brief overview of what our hypothesis and what we're trying to do was basically we were trying to block, to isolate, completely isolate current or voltage control to the other side of the thing. So to start, we wanted to measure how it goes through each block of the section. So anything, but to start that, to measure anything within the system, we had to make sure that whatever we're doing within the system doesn't leak. So current or voltage doesn't leak to the laptop or like the PC or the patient. So to start, we had to completely isolate, ourselves, the power through the thing, through the system. So there's no direct path from the current to for the current to flow from our PC to the patient. And conversely, if there is too much voltage coming into the system, we could lower it to where it doesn't affect our circuitry in the system. So our main objective of the research was to implement a completely isolated power monitoring system so that we can, the robotic autonomous wound closure can detect the current through each block and how much power is going through each block. So first, we wanted to measure the current and voltage across each block, how much power is going through each block, and to optically isolate the power, eliminating a direct path flowing from the device to the patient, so there is no harm or anything done to the patient. So so this is my my process on how I got to that conclusion. So first, I using a voltage to frequency converter, I measured different voltages and its corresponding frequency to get a directly proportional line. So whatever frequency and any voltage we put in, we get something proportional to it. So with the frequency to voltage converter, the working voltage for the converter was 13.5, which you can see for the PC. And I had a controllable input, which was 0 to 10, and the frequency that was supposed to be outputted was supposed to range from 0 to 26 hertz. And yeah. So this is the result of this. So as you can see, it's directly proportional, and I stopped at 8 because that was how much frequency was supposed to come out, and then any number after 8, it just was giving me an error because that's how much the board could operate at. So we did this to we did this because when we are measuring the voltage that's coming into the system, we want to obviously isolate the measurements. So when the device is at a high voltage and it's connected to the system, we use the shunt, which is also connected to the measurements, the system, and it creates a low resistant path for the current to go through it. And depending on what's inputted, you can choose which one to use so that it doesn't affect the circuitry within the system. So also, whatever is inputted into the system, regardless of what's going in, it's directly proportional. So whatever we read from measuring the blocks, it wouldn't really matter because we are trying to, when we use the shunt, we're getting the voltage down to a level where there's no damage done or it's affected within the system. This is a shunt. We also use an optocoupler to eliminate the direct path that flows from our device to the patient and vice versa. So there's no direct path within for the power that goes to the base of the transceiver. So the only path that this could get to the other side is through an LED light. And there's no way for the transistor to turn on without burning. So I repeated the exact same procedure with the voltage to frequency, a frequency to voltage conversion module. I connected the VCC, and then I had a controllable input from 0 to 10, and then the frequency was supposed to range from 0 to 10. The voltage was supposed to range from 0 to 10 volts. Unlike my first results, I kept going after 10, and as you can see in the results, there's like a drop, and then it continues to go up direct proportional to the frequency. So yeah, the board that I used, the voltage to frequency conversion board, it only goes up. It can only take up to 10, and after 7, that was the maximum it could take. So after that, it just dropped. So at 8, it dropped to 8, and then it just went up after that. All right, so using that view, I created analog input voltage, and with this, I used the NI DAC to program a frequency measured program where I connected a voltage into the NI log. It had channels, and using channel 1 and 4, I connected a voltage, and then I used the tone measurement to basically measure the frequency of the voltage that's going into NI after that. And this is the result. whatever I was getting from the voltage that was being inputted into the system. Okay, so for our future development, we wanted to connect, to have a connection block. So basically, I had to use a separate optocoupler, a voltage to frequency converter, and then another frequency to voltage converter. So we wanted to connect everything together, a switching block that would connect everything together, so it just does it by itself. So it measures everything using multiplexer, and then it just does everything automatically and then starts over. Okay, so also we wanted, so the robotic enclosure is supposed to do a lot of stuff without a person actually doing it. So also we wanted to input a temperature monitoring, just like the power monitoring system that would be supported by the system. And then also one of the future developments that we wanted to have was like whenever there's a power offset that's going on within the system, it could alert us and let us know like what's going on and how we can fix it. So basically, I had to keep starting over because the boards that Professor Curry was giving me wasn't working. So I had to keep stopping and waiting for us to order a new one to keep seeing the trainers, and also learning how to use LabVIEW. So Professor Curry gave me the book, and I had to learn how to program and how each block works.
Okay, so my project was microplastics. The official name is the investigation of microplastic extraction from road dust samples. Also, my name is Cassandra Melendez. I am currently a rising sophomore majoring in civil engineering. And one aspect of civil engineering is environmental engineering. And my advisor was Dr. Hunter. Okay, so the basic overview of this project is intro, like the materials and the process of identifying the microplastics, as well as other conclusions and future works. So just to start off, microplastics, if you didn't know, are small plastic particles measuring to 5 millimeters or less that result from the breakdown of larger particles as well. So they are categorized in two sections, primary and secondary. So primary is essentially just basically microplastics that are created from cosmetic purposes, say like makeup or anything like that.
as well as just industrial use as well. And secondary is just the breakdown of larger plastic particles. So you can say from like a water bottle or anything like that. And the way that microplastics are created is that it's basically through weathering down of just say like wind abrasion, or just if you just like process it and you get these small particles in there. And also, so the reason why this is important is because currently we are in an industry where plastics are created over basically too much, and then we can't basically, you know, process them down or just make sure that we can get rid of them. So right now there are so many that are in the ocean or just in our environment that you can see nowadays, and we haven't been able to just properly just break them down or get rid of them. So this is why we are focusing on just how to extract them from, say, soil samples or just anything in general, because if you think about it, these are in our waters, and all the animals that live in there are absorbing this type of stuff because they live in those environments. And then afterwards, then we eat them. And like essentially that's what happens, is that we have the plastics inside of ourselves as well. And that isn't right, you know, it isn't healthy. So that's why we're focusing on microplastics. Okay, so the objective is just to investigate the effectiveness of various techniques that we extract plastics from, because currently we don't have a standard one that would allow us to efficiently just get them out. So far we have various processes, but we're still experimenting with that. So we're also, afterwards, once we extract them, we're also focusing on identifying them, because there are so many different types of plastics out there that it's hard to look at them at its microscopic level. So this is just an example of just methodology. So this is the one that I'm going to be focusing on, which is that we start with digestion, separation through overflow, and filtration. And here we also use another method called desiccation, where we put it in this large apparatus, and we allow it to essentially dehydrate the soil samples that we have, so that we can then further look at them under a microscope. Okay, so here are some of our materials. So we gathered soil samples or just roadkill samples in our local area, say parks or just any roadsides that we see any samples available for. And we also have some of the other equipment that we use, say like the Fenton's reagent, as well as hydrogen peroxide. And we also have the sieves that we use as well to separate the soil from, say, like rocks or other large like items that were in there, so it would be easier to focus on the project itself. Okay, so the process. So first we collected the samples, and we made sure that there was no contamination by putting aluminum foil over them, just the risk of other microplastics in our or outdoor environments. So we put it through this sieve that we have right here, and afterwards we put it in a beaker, which was then basically digested with Ben's reagent as well as hydrogen peroxide, because this allows the organic matter to separate from the actual sample itself, so it's easier extraction process. So afterwards, we did three beakers for each one that we did. So we had a total of 3 samples themselves. And afterwards, after we had carried out that chemical process, we allowed it to set for 24 hours. And we also covered that with an aluminum foil. So, and also I just like to note that throughout this entire process, we made sure that there was no contamination as possible. We wore lab coats that were made of cotton. We wore gloves. We made sure that everything was covered with aluminum foil, just to be exact. So after we had the sample for 24 hours, then we allowed it to be transferred to an apparatus that we made. So if you just see right here, take this place. Okay, so this is the apparatus that we made here. So if you just look at that, this is what we created. I'm just going to pause it right there. Because first, what came first is that we transferred it in there, and then we filled it up with deionized water, just to make sure that there weren't any other contaminants. And afterwards, we placed it in this apparatus that we created ourselves, and we put a stir rod in there so that it can magnetically be mixturized using this type of scale. So afterwards, we had allowed it to be spun for 4 minutes, and afterwards we allowed it to rest for the same amount of time, and we did it for a total of 3 times for each sample that we did. So it took a while. So basically, this is the sample of the process that we did it here. So see, you can hear like the samples being separated, so that then they can be overflowed to the top, and then we can allow it to have density separation through overflow, which I will get into. Okay, so afterwards, after we did that process, we essentially did overflow, which is back here. So basically what it did is that it allowed the particles to go all the way to the top, and then we had used a wash bottle to then fill it up to the top, so then the microplastics and also the other organic matter in there to be separated from the actual sediment itself. So this allowed just for easier extraction just to go from there. So afterwards, then we filtered it out. So after overflow, then we had filtered it out through a sieve, a 500 micron sieve. And then we used this vacuum pump right here to just separate it so that we can get this result right here. So essentially, this vacuum pump would suck out all the liquid in there so that it could leave a residue that we can then look up under a microscope. Okay, so we do have a couple samples of just the microplastics themselves. Be aware that there are other particles in there that also could be potential just microplastics or just other samples that we found in like the soil samples themselves. So here is a diagram of just how microplastics are identified. So this is in a set one. There are many out there that have different methodologies out in order to identify it. So like say for instance, this categories is source, type, shape, and erosion. As you can see, there are various descriptions for each of them. And we also have like, consumer product fragments. We have pellets, like micro pellets. And we also have for like unweathered objects or just any type of transparent ones as well. So here is one that we found in our sample. This is, I believe, from the one from actually my vicinity. So here you can see that there is a small, like, this is basically 724 micrometers of this sample right here. So just looking at it from my perspective, this would look like, perhaps maybe something from like a branch or anything like that. And then we also have some other ones in there. So as you can see that from here, it's just like, it's very hard to identify them because there are so many other things that are in these samples themselves that it's hard to just separate them from that and go from there. So we have some right here, like that right there could be a potential one just by looking at it. It looks like, has a red like line over there, so it could be something of a plastic. So this is one of the issues that we face, is that it's very hard to identify these microplastics, especially if you don't have a very detailed background around them, if you've worked for them very long or anything like that. So given that I was given for like 5 weeks just to focus on this, also another conflict that I face is just to learn microplastics and how to identify them. So here are some other samples right here. So as you can see, this one's more noticeable compared to the rest of them. You have just this blue little like item right here that could be a potential like microplastic or anything like that. And also in some of our other samples, we found a lot of glitter. A lot of glitter that was very noticeable because it emitted a certain color to it, almost like this, but more, I guess, more noticeable. And then we also have some here, but I wanted to put this one here because this isn't a microplastic just by looking at it. So if you can see from here, I know it's not very clear, but like you can see how there's very uneven textures to it. There's like gaps in there. There are like very like long rigid things there. So this looks like basically like organic matter, maybe something from like a leaf or anything like that, just by looking at the textures, because microplastics don't necessarily have like extensive details in that are compared to like say something that from like a tree or anything like that. They have more complex structures compared to microplastics because they are just natural. And also here we have is just a sample. So this from my just my investigation is that I believe this was from the sodium chloride that we had, which was allowed to just use sodium chloride to just create a more like reasonable sample for that. So here you can see that it got in some of it too. So you can see like all the textures in there. So obviously this isn't a microplastic because it wouldn't give out this sort of color. So there's something like glitter or anything like that. So these are just some of the samples. We had many more. As I said, we did like at least like a total of like 9 samples in general. And just the filtration process allowed us to generate a lot of samples that we looked at. So we had a lot of information to just gather from there. Okay, so for my conclusion, I said that there are many areas of improvement for this method of extraction from microplastics, especially the one that I investigated for my project. Just say like just some examples. Obviously, I used just to use an overflow as well as filtration process through a vacuum pump. But there are other ones as well, like desiccation, how I mentioned. Other people focus on focusing on wetlands or other sediments from different areas. Also, I said how there was a tool that was in our research that was very helpful. It's called the Transform Infrared Spectrometer. So this is an example of it. We weren't able to have access to it within our time frame. So this is just another thing that we have right here, say like this. As you can see, this is a sample right here. But if you look at these like really small specks right here, you can tell like those are plastics because they're giving up a certain like, I guess like a display or anything like that to them compared to like the actual sample themselves. So this tool right here is a very good one because it's been saying that through research that it's very, I guess like very efficient compared to other ones. And just future research, further investigation will allow us to have an establishment of a proven procedure for microplastic identification and extraction so that we can then reduce the amount of plastic in our environment and essentially. Also, I'd just like to acknowledge Dr. Hunter for advising me throughout this and as well as providing the assistance. Also, Michael Wang, he was also another student who had helped me through this project. And of course, Keith McKenzie, because he helped create the tool that we use for this project itself. And thank you, and let me know if you have any questions. Yeah, so technically from my end, I did do it manually. It's because of the accessibility of like equipment and tools. But research has shown that like I said, the FDR short is basically this machine that provides, if you put a sample in there, it shows you like the waves essentially that are transmitted from the microplastics themselves. So once you see the wave that it emits, you can compare it to other ones that have already been investigated, and you can then go from there to identify which plastic it is, like polyethylene, polystyrene, which is styrofoam, or PVC, and then you can go from there. Yeah, like that we can look into. We were also considering for like another machine like I mentioned, the FDR. Yeah, like that's another thing we can do like maybe for next year that we keep that in mind, and as well as like reach out to other companies that would have those tools to use. Yeah, and we're also yeah, it's all a process. Yeah, so that was definitely one of the main things, like some are like desiccation or the even this method. They mainly use
Hi, I'm Jessica Sell, and I researched this summer the changes to the New York Codes, Rules, and Regulations, Part 360, and the resulting effects on solid waste management and data analysis. So, just begin with, what is solid waste? This is the RCRA's definition of solid waste. But solid waste is basically any product that comes from a facility, commercial, so it could be from dirt to sludge, to leaking to grease, and all that stuff. So you could find it in commercial, neighborhood, communities, and solid waste does not just have to be in the solid material. So solid waste could be liquid and gassy, it could be semi-solids, and what we researched this summer was how to manage it correctly. So solid waste management is collecting, treating, recycling, and disposing of solid waste that is being removed from a location and the possible reuse of it. So if you could bring it to somewhere else and they can benefit from it, that'd be great. So regulations have been revised. They've been going under revisement since 2017. And it's been an ongoing process because COVID broke out, so a lot of people were redoing their mulch, their backyard, and facilities were taking in more debris and more products than they usually would. Additionally, since the rules were becoming more strict to ensure human health and the environment was being protected, a lot of facilities brought up concerns they had, and then one company even did a lawsuit against the New York State. There's a lot of things that changed as the regulations. I'm going to focus on two main ones because closing facilities and operating facilities and a whole bunch of things changed. One big change was the solid waste fill material. Beforehand, fill was just soil, dirt, gravel, concrete, all that could be broken into three general categories. So general fill, restricted use fill, and limited use fill. These are very broad, so a lot of people didn't want to use fill that was restricted use if you were going to put it on like a playground because no one wants their kids playing in dirt that's restricted. So these topics were recategorized into fill type 1 through 5 and then had more strict criteria so they could be reused for different purposes. So fill type 1 is just any use, general fill, nothing's noticeably contaminated, and going all the way to 4 and 5, which are more contaminated but still safe to use, but more restricted on where they could be placed. So fill 4 and 5 can not be placed in Nassau or Suffolk County, along with the New York watershed region and Westchester County. So it very limits where it could be used. So this caused problems for facilities because people don't know if they want to bring in that kind of fill because they can't really put it a lot of places. So this is what we're looking into, where it could be brought and how it could be properly managed. Another thing that changed along with the regulations was permit process. So a lot of facilities were just registered, and they only had to fill out paperwork that was 1 to 2 pages long and didn't have that much paperwork to submit. Now the rules became stricter, so a permit application will have to be processed. So permits could be up to 600 pages that now facilities do not want to be bothered with to do. So now facilities will have to create engineering reports, do regional and vicinity maps, control waste plans and noise assessments, and make sure their roadways are accessible in all different kinds of weather conditions, and that they're not bothering the neighborhoods. They have to have site plans. So this creates a lot more work for facilities just to safely manage solid waste. While focusing on the fill material, there's different chemicals and testing procedures that need to be done to test the samples and see what fill type they are. This is the EPA's official collection of methods that can be used to test what chemicals and what samples are in the fill. So there's over 219 different methods, and these collection of methods will state what you're testing for, how long you want to have the sample before you test it, and how long it'll be held for, what kind of container you need to have. A lot more detail and criteria is going into managing solid waste. So these regulations can be used for air sampling, stack emissions, waste characteristics,
leaching and extracting methods, and sample preparation. I focused on the 8 Becquerel metals, which are heavy metals that are seen in the soil samples, very dangerous and hazardous to human health. And the main goal is to manage solid waste to benefit human health. So arsenic, barium, cadmium, chromium, lead, mercury, and selenium, and silver need to be regulated closely. There's all different kinds of methods that can be tested for these metals, and some methods could be used to test all of them, some are limited, so picking the right method is very important. So while doing my research this summer, I worked with Dr. Hunter along with Walden Environmental Engineering. I worked with Josephini, and basically we were coming up with plans of how the changes would affect the environment and how it would also affect the environmental industry in general. So how consulting firms could help facilities operating. So Walden Environmental Engineering works with tank and fuel management, testing and system evaluations, on-site testing, annual reports, permit applications, so they can help with the new 600 pages that facilities will have to submit now. And annual reports will be good because they are collected, and you have to keep count of how much debris you bring in, how much branches, brush, and all that kind of stuff needs to be recorded every year. So they work with mulching facilities, fill material, transfer stations, grate trap, collections, compost, and construction, demolition, and debris. So I actually got the opportunity to go to a mulching facility, and here in this picture, as you can see, I got to learn how it works, how much they can bring in, what the regulations are that a site needs to have. And this site was actually being reevaluated because they wanted to work with construction debris and mulching, but they wanted to break it into 2 different facilities to make it easier to manage and less contamination. So the logs are brought on the trucks, and the trucks are then dumped the log. Each pile needs to be within 10 feet apart of each other, and they need to be in wood row formation. Then they are inserted into a chipper, and then the chipper will just create wood chips. And then depending on the size, if landscaping companies want to use it or who's going to use the mulch, then they can be processed again, or they could stay where they are. And then the piles then could be dyed, as seen on the left-hand side, and they could be brown or black. But keeping these piles like this also need to be overturned to prevent the wood from being too hot in temperature, and it needs to be in like a triangle formation to prevent runoff, so the water does not leak in when it rains and does not leak into the water of the soil and the water table. So here is a picture of the wood chipper that the logs would be put in and then it would come out. Here's another pile here, and if you could see the 2 piles there, as like they don't look at this angle, but they were 10 feet apart. And a big thing that they can't have is like no still water on the property. So if it rains one day and a puddle fills up, that's not allowed. So Walden Environmental engineers went out, they assessed the site to see if everything's going along with the regulations and the new rules. So since all the rules are being updated and regulations are changing, environmental data management is very important because facilities are going to be required to sample more data, collect samples more frequently, and then keep the data up to 3 years. So one software I researched was Equus, which is created by EarthSoft. And this would be to improve the quality of field and lab data. So you could take a Microsoft Excel, plug it into the system with all the information from what they've collected throughout the year and all that, and create the needed reports for the Department of Environmental Conservation. And then all reports needed based off if you needed to collect the information. So this one had benefits because it was easy to use. The only thing was the graphs were easy to make, but you had to manually input your scale for your data. Also, the program also produces its own errors on times, and then identifying the errors could be hard, along with contacting customer service for assistance is a little challenging, so they take a little bit longer to answer. Another software I researched was EnviroData, and this was created by Geotech Computer Systems, and specifically Dr. Dave. This program came with all the bells and whistles, all the built-in options anyone could need with the built-in set price. Equus had it for additional cost. So this was a very easy to use interface. Program entry was very straightforward. It would have a data corrector, so if one of your chemicals was over a limit, it would mark it red, so you can notice like, oh, that's a red flag, it needs to have that checked out, and maybe has to go for resampling. There's a lot of built-in operations. The customer service was very easy to talk to. The only negative part about this program was, since it was so large, learning it could be overwhelming. So I would say they have a bell-shaped curve. So once you basically figure out and you're not overwhelmed and you take the menu-driven interface easily, it's easy to work with and manage your data. I would just like to say thank you to Dr. Hunter and Josephini and the School of Engineering for my opportunity this summer, my references, and thank you. Does anyone have any questions? It's just one of the RECRA medals that the resource conservation. Yeah. The limit could be found in a table that I had access to, and all the limits vary based on the chemical. No. Standing water. It's because they don't want the water to stand in the property and leak into the soil and then contaminating the ground. So they want it to run off the property, so none of the material is going to be like reused. It's like contaminated. And then that will make sure the runoff goes all the way to the end of the property.
Awesome. So I'm Logan. I'm a junior industrial engineering student. I work with Dr. Roha Murillo for my ASPiRe research project. We applied ergonomics to computerized design. So this is the presentation content. We're going to run through some introductions, methods, results, discussion, conclusion, and acknowledgements. All right, so I want you to think about what is the best computer mice that you've ever had. What did you, maybe you were using somebody's friends, somebody else's, and you're like, wow, this is really nice. What made it nice, and what would you change about it too? So you might be like, oh wow, this really fits my hand, but I want my thumb more supported, or something like that. The scroll wheel is kind of funky. That's kind of what we're going to analyze. So computer use. About 89% of US households have computer desktops, and the most used human-computer interacting tool is the traditional computer mouse. Workers average more than 6 hours a day in front of computers. So not only are you right here, you guys all have a laptop right there in front of you. You're working at your desks, students are working at their desks, and you're working at it for an extended amount of time. And this is almost everybody. Everybody has that either at home or at their work. And musculoskeletal pain. Chronic primary musculoskeletal pain is defined as chronic pain in the muscles, bones, joints, or tendons that is characterized by significant emotional distress or by functional disability. Episodes of musculoskeletal pain affect approximately 47% of the general adult population. Anytime that you're typing away and then your hand cramps up, that's musculoskeletal pain. That's affecting you right then and there when you can't work anymore. So previous research, they looked at a lot of different researchers used SEMG to analyze muscle activation, and in the hand and wrist region when you're using that mouse, there's a lot of these different movements that can be detected by SEMG. So when you're utilizing that mouse, they kind of had the frame of mind of thinking less muscle activation meant less risk for carpal tunnel, because that extended amount of time with the muscles being activated in like the 6 hours plus a day does cause carpal tunnel. And then they use common computer tasks, so dragging, clicking, the accuracy and speed of those movements are definitely indicative of a good computer mouse. And then we applied ergonomic design processes and we made a lesson. So our aims are to apply ergonomic principles to computer mice designs, give hands-on opportunities to undergraduate engineering students, design an activity involving diverse technical skills, and create functioning communities. So we decided to start with a Logitech brand M325 model mouse. As you can see from the top, you can see those finger grooves and that really circular shape. That fits really well in the palm. I wish that you guys could try one of these up here, but I can't pass them mouse too far around. And then we have the ergonomic features already there, and it's really accessible too. So it's between $13 and $16. A lot of people have it. I had this mouse even before I started this research, so it's definitely really popular, and that's why we chose it. So we had this proof of concept. On this bottom row, you can actually see it on the table here. This is the mouse broken apart and spray painted. The reason we spray painted it is because the scanner had to use lighter colors. It uses a projection of light. We'll see it later, but so we couldn't actually scan it at first because of the darker colors. We spray painted it, and then we actually had this. This is straight from the scan. It was a really accurate model, and we had that proof of concept for how detailed we could make the mice. These are the internal circuits. This is what actually makes the mice work. The battery fits in right here. So we knew that we wanted to reuse this because I am not an electrical engineer. I cannot really make one of these, so we decided to repurpose it from the Logitech brand, and it's really cheap too. So you can buy like 6 of those and have a whole class out there. So this is the universal base that I designed. I used AutoCAD and Blender to make it to precisely fit this circuit here, and then students wouldn't have to worry about this. They would just focus on the shell, making what your hand is actually touching. That's kind of what I refer to the shell as, and they can apply ergonomics best there rather than worrying about making it functional with the circuit. And they only have 4 to 8 weeks to do this. So in between like printing time and scanning time, I didn't want them to worry about the circuit and stuff like that. So this right here, this is a few of the examples of the printing errors that we had. As you can see in this slide too, we had a lot of different iterations. So I went through this design cycle a few times on a few different universal bases, and the final one that we have is right up here. But you can also see that the printing errors, we really sometimes didn't know why a file didn't print right. We have some of the trays up here, and sometimes I would send a file to print and it would be fine, and then for a different printer it wouldn't work. So there was a lot of like maybe file corruption. I was using Gmail a lot, and we thought that transferring it via that way might have been corrupting it. So I was actually walking in between atoms and weed with a USB drive, delivering files to different professors, and along with software updates. So Blender, the program that I was using, was the most up-to-date version, and if we were using software for a 3D printer that was a little bit older, it might have been a little bit more challenging for that file to transfer over. So this is the total like product of the lesson plan. They only have to worry about that top left corner, that shell, the ring and the circuit fit into here, and they don't have to worry about making that universal base. So that is what makes it functional, and that top left corner is what makes it organic. So this is the lesson plan. They'll have to research, make clay models, 3D scan, edit, print, and hopefully make it functional. So for the student research part, I really enjoyed my time during ASPiRe, and I think it really proved to me a lot of different things. So I'll talk about that through the lesson plan, but they need to develop an understanding outside of the textbook. They need to understand that things are really being applied, especially during in research. Things are applied in really niche ways that can be really cool to explore. So I wanted to simulate that part of the research, and reading comprehension is really important. I think that there's a lot of focus on math and stuff like that, but being able to read, understand, and apply research is also really important. So then they move on to clay models. We used air dry clay. It dries in like 2 to 3 days, so it's really easy for turnaround. They're going to be applying those ergonomics there. We have some examples of the clay models that we did, but this one right here, you can see kind of like the finger grooves. I know it's a little bit hard. Some finger grooves right there, and you can see like the hand fits exactly like this, and you just lay it out, so you're not putting tension on the fingers holding them together. This one is also pretty ergonomic, has those finger grooves. This is an example of a not really ergonomic. It's actually perfectly flat, so it doesn't contour to the hand at all, and doesn't really reflect ergonomic knowledge. So we definitely want to use that as maybe something to avoid, and these two to kind of look towards as examples. And to specify, it has to fit this internal circuitry. They'll have access to universal base to make sure that their mouse fits right on top. And then constraints. You have to have ergonomic features. If you make a flat mouse, you are not going to do well on the lesson. This is the scanner that we used. This is actually the product picture, and you can see how it's structured there. There's 3 cameras. You can see it a little bit better here. Scan using light onto this mouse here, and it just projects light and takes many scans. I did an average of 3 scans per object, so it would go and rotate all the way around. We do have a tutorial for the students, but I think it's really important for them to navigate it independently and have the skill elasticity to make their way through an unknown program and an unknown product. All right, and then they have to edit the scan. So you can actually see some extra additional vertices that were picked up by the 3D scanner. Those will have to be edited out for the 3D print. And I actually used little bits of clay to prop up some of the mice for better scans. And they would also have to clean up some of those. And it would have to be saved as an STL file for those 3D printers. This is a video. This is just past Logan. We have the volume. And here we have on the podium. Volume up. Podium volume up. Okay. All right. Let's see. This is just past Logan. Navigating Blender with you. And here we have 4 different pieces that make up mouse for the. So sorry. Okay. So I'll let the video play. And then I'll just talk through what I'm doing, because no one definitely everybody. Okay. All right. So this is me navigating Blender with you here, and here we have 4 around some of the objects. This is what a functional ergonomic. So there's this universal base here. So as the ring as well. These 2 right here are a little bit harder edges. So the structural itself are definitely and then for some of those had by me. So I made it so the dimensions of the circuit would fit in here correctly, along with the laser for detecting movement. The student shell will actually click finger shells there. This has the bottom will make it so that it's clickable and those access circuits get the access adjusted. And then I'm just going to pan over. Right here are the 2 functions. So students only have to worry about 50% of the. So these are all the functions on the left side of Blender. So if students aren't able to sculpt really deep finger grooves into their mouse, they'd be able to do that in post edit. So that was the big draw of Blender, And then hopefully they'll be able to print, again, with some technical difficulties. This is an example of a mouse that was printed fully to scale. This is the same file, actually. And then this is its counterpart that was printed left-handed and really, really small. It's quite cute, but not very cute for research. So there are some different things to work out of the 3D printing process. And you can see some support materials still on this one. Acid baths are really important, especially for the class, because they wouldn't be able to chip away during time in class. The acid bath makes it really fast, just 6 hours, and it's really clean. Yeah, and to discuss for the conclusion, I think that for the Science and Innovation Center that we have coming up, we have a lot of really awesome resources in this building and in Weed Hall, and those include the 3D printers. And I think that 3D printing, my experience with it, has made it very clear it's something that we can use in all of our departments. You get a proof of concept in 6 hours. That's crazy. And so I think that we can really utilize that a lot better with 3D printing training as well. So I know we have that new business coming up. I don't know if there's plans to transfer some of those 3D printers over there, but allowing students to have hands-on time with it and actually working through the process themselves, I think 3D printing training would be really awesome. I think that I could have maybe gotten a little bit farther understanding 3D printers before the process, and even having a certification program or something like that where you're able to do internships or co-ops with 3D printing companies. That's the forefront of the future, and you can make this adjusting either computer mice or pens, or for people with disabilities, right? If they need to access something in a different way than the majority of the population, you can make those adaptations with 3D printing. And it was really quite exciting to be able to take part in the ASPiRe project. And I would have never seen myself, even 2 weeks before the end of the semester, being able to do this and having all this in front of you guys. But again, I would like to say thank you. And so in the future, I'm hoping to make a functional computer mouse. I was so close, but some of the files were getting a little bit more corrupted than usual at the end of the 10 weeks. And I got to see industrial engineering really, I feel like, for the first time. That's my own major, and I actually got to see that as part of the research project, applying human factors and ergonomics. Future work, inserting this lesson plan into either Engineering 19, 119, or 128. Both of those deal with worker production systems, human factors, a variation of both of those, and applying this process to different labs. Yeah. And I want to just say thank you to the ASPiRe benefactors, Dr. Obani, Dr. Albers, Dr. Zhao, Mr. McKenzie, and Mr. Sarah. Thank you. Yes. So in my research, I didn't actually find any of those. A lot of the research was on like adapting different mice like techniques for like maybe clicking buttons in different ways, which might be in sort of like for one person like with a disability of like of not being able to press really well, but I didn't really find that in the research. Yeah. Yeah, we definitely, so we started out with really just knowing we were going to do research on computer mice, and we were looking about how to make custom computer mice for people. They say that carpal tunnel can be reduced by even just having different sized mice. If you're trying to use a mice that's too big for you, you're going to be straining your hand a lot more. And if you look, all of the computer mice that are provided by Hofstra University are these. So if you look at these ones, this is the prime example of something that has a little bit of slope, but are all our hands going to fit this? No. So it's kind of hard to be like, oh, we have cars that are adjustable for seats for somebody who's taller, somebody who's shorter, but we don't have mice that have somebody with smaller hands or bigger hands. Yeah. Yes. Yeah, for sure. So ergonomics, I did actually have a slide on ergonomics before. I'm regretting it now. But what I came across, it's also called human factors in the United States. So that's why I know for Dr. Rojas, his class is called human factors, correct? So we call it ergonomics because the rest of the world did it, and I thought it was better for the presentation. But it's making, for me, I define historically, people have been made to, like in factories and in different processes, they have to fit themselves to the machine, and that's where we get carpal tunnel and repeated stresses, worker injuries, and things like that. So if anything, to make the human's life easier and fitting into that way. Yeah, we were looking at the NASA TLX. Yeah. Yeah. There's definitely that trade-off of like having a really ergonomic mouse, but if you can't use it because it's like a joystick or something, we have a mouse like that actually. It's like not really worth it if you're not going to do it with them. They do make it. Yes, they do. Yeah. Yeah. Yeah, for sure. It was definitely pretty challenging with that. Yes. Yeah. 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 So we actually have, we were able to purchase a few different really unique mice, including one that was a joystick. What was one of the other funky ones that we had? I'm trying to remember. Yes, and it actually, it curves and you have to click it into place. But there's a lot of really unique ways, including like styluses as well, to navigate computers. But the thing is with learning curves is some people have a really hard time using that trackball. And even having your hand like this, I don't know if you've noticed, but you can actually feel your arm getting more tense. So having that too much ergonomics or having too much of an inclination can actually affect your arms here, because even having the posturing allows us to get into like how to posture somebody and train somebody to have the right posture when they're working. Because if you're here and you're relaxed here, or if you're like leaning really forward, right, you might be affecting your back, but it's because you're using the mouse. So there's a lot of different ways to explore that. And the trackball is really cool. Actually, Steve Jobs wanted a mouse that was designed to like use it on machines. Yeah. So that was the original mouse. Yeah. Any other questions? Yes. Yeah. So that's what we did when I scanned a mouse. My process was moving from here. So I would scan this one. I could actually edit it in the program for the scanning and get off that extraneous material more often than not. And then in Blender, I was contouring more. I was adding some different indentations. What do you mean by that? Yeah. Yeah, I would love to use different programs. Yes. Yes, absolutely. I have some of those right up here. But the reason we chose Blender specifically was because of they have that sculpting ability, and you're right, their focus is not on. Oh, really? Okay, interesting. Noted. Thank you. Any other questions? Oh, awesome.
Michael, I don't know if you can hear me. I'm standing at the podium. It's Liz. If you can hear me,
Yep, I can hear you.
Michael, if you can hear me, screen share your PowerPoint. We're running a little bit late here, so we might be a few minutes getting started. Perfect. Listen, if you wanna call my cell number, I'm gonna give you my phone number. It's 516-816-2182. That way we could chat for a second before we get started. Everyone's finishing up their lunch. Like I said, we were running a few minutes late. Again, it was 516-816-2182. Hi, Michael. Thank you. I should have exchanged cell numbers with you just in case we did need to speak. But we're all set. Your PowerPoint's on the front. I actually just. Oh, I have you muted. Sorry about that.
Can you hear me through the computer right now?
Yeah, I am. I can see. No, I can't hear you through the computer right now. I have to go find Alex Rosenberg. Just hold on 1 second. I can see him. Just leave yourself unmuted though. Okay, you're unmuted?
Yep.
Oh, can you do a test now and see if I can hear you?
Oh, test 1, 2, 3.
Okay, yeah, I'll be right back.
Okay. Okay. Mhm.
So I have him on my phone now, so here is his slide, so we're screen sharing it, but how does the room listen to him?
Does the room listen to him? Where is he? This is him.
Yeah, and this is
He's
his
at his
phone.
house.
Yes, I'm on the phone with him, but I can't hear him speaking. I'm gonna keep looking for Alex. So you're informed if there's one scene for him, let's get the show rolling.
We're working on it. Check, check, check. Better than me, probably quicker than me. Okay, so he's unmuted.
Okay. I could hear them before. Now I can't hear you. Oh, wait. Sorry. Oh, I turned my. Never mind. I can hear them.
He can hear us, we just can't hear him.
Yeah, I just turned the volume on, so I didn't hear you twice initially.
Oh, okay. In worst case.
Test.
Oh, yeah.
Okay, I can adjust the volume.
Can you do a test, Michael, so we can see if everyone can hear you?
Oh, yeah. Test. No, I shouldn't. Yeah. It even says that there's voice coming through the mic.
It says there's voice coming through the microphone.
Tell him to turn his mic volume up.
He's,
Okay, I have it all the way up. You can't hear me through the computer at all?
No.
yeah, we'll get it working.
Okay. I'm gonna see if I can stop my share and edit my
not sure what we can do on our end.
You know, in a worst case scenario, I can hold my phone up to the mic in the room. Like, I'm being serious.
Oh, actually, he could dial in by phone.
I'm sorry. Here, look. I don't repeat it.
Hi, Michael.
Oh, dial in by phone on Zoom.
Yeah, you can dial in by phone, and join the Zoom meeting that way.
Okay, let me see if I can see that on here. There should be an icon on Zoom. Sorry, just going through this.
Because even before the Zoom couldn't get in, we had to make noise. Or couldn't get it louder. The back is the same as this. So this is the lab.
What is lab?
Lab means this mic. Okay. Handball, that's this one. And then this is.
Is there anything that does the computer? It's this one. Is that computer noise?
That's two. No, the computer would be. This one.
It's before the computer itself was very well.
Yeah.
Since we're trying to play a video.
So I don't think I have the number right now. I'm trying to find it on here. I hit the little info in the corner and tried to copy the link. I don't have the actual phone number.
That would be this.
Okay.
So this one controls.
So maybe all you need to do is turn that louder.
So Alex is having a dial in the room, and do it that way.
I don't know if Alex heard me, but I couldn't find the number to. Oh, okay, cool. All right, thank you. So you can all hear me now?
Yes, we can hear you.
Thank you.
It's probably going to be, I don't know, 3 to 5 more minutes. We're just running late with our lunch.
Okay,
Michael?
just let me know. I'll mute myself for now.
Okay.
everyone. I guess we could get started, right? So I'm Dr. Fu from the Department of Computer Science. All right, so it's my great pleasure to introduce Mike Raymond, who has been working with me almost 1 year on this particular project. But before we get started, let me ask you guys, how many of you got virus scanners on your computers? Oh yeah, I guess all of you, all right? So Mike's project is about can we, in the future, all right, probably not 10 years away, all right, can we, in the future, eliminate all the virus scanners on your personal computers and servers? All right, so Mike, are you ready?
Yeah.
Okay, let's get started.
All right. So, hello everyone. Today I'll be presenting a project that I worked on with Dr. Fu this summer, proving malware freedom with zero knowledge. So let's get started. So, what you may or may not know about these two very popular symbols, Gmail and Microsoft Outlook, is that they actually read your emails. Whether or not it's actually a person reading them doesn't really matter, but they have access to your emails. They can always read them. And a big part of that is for malware detection. They want to make sure there's no viruses in your email. I've personally had experiences with this where someone misses class or something, and as a computer science major, we're sending each other files on a regular basis. And I tried to send someone on like a JavaScript file or a PHP file, and it'll flag it and say that this might have a virus in it. And that's to protect us, it's to protect the server, it's to protect the recipient, make sure that there's no viruses anywhere. But what we want to do is actually make it so that you don't have this, so that your email actually comes with a proof. It'll just say that it's virus free, and then we never actually have to read your email. We don't have any access over your email. We can just encrypt it, lock it away, and never look at it again. What this proof would actually do, though, is it's actually very small, 288 bytes. To put that into perspective, for verification time, it would take you 2 milliseconds to ensure that this is a safe file. Most malware detection systems, I think, run around 2 megabytes per second, which is very slow. If you have a couple gigabytes of a file, it could take like hours. So this will take 2 milliseconds regardless of how large this email is. But how? So let's work into it. So first off, we have our malware detection automata. This is actually the malware scanner. This is where we're searching your file, which we do read your file one time. It's not us, it's actually the program itself. We never have any access over your file. It scans your file using this fancy algorithm called an Aho-Karasik string matching algorithm over this ClamAV virus signature database that will essentially have a number of different strings or words. In terms of this, there'll be like bits and bytes, and it's not really readable by humans. For simplistic terms, you would have like, if a bad word was his or her, you would write his is one line, her is another line, and you would try to match each individual character to see if it passes or fails your string matching algorithm. And by definition, it is a deterministic finite automata, which means that we have accepting and rejecting states, and we want to make sure that we can find find any viruses or know if they are there or not. So what does this really look like? This jumbled mess. So what this actually is on the left you can see what is an accepted and rejected state. And essentially we would feed in some string, some word into this. To keep it simplistic, I've used hers, his, and she as the baseline for the automaton itself. And if I was feeding in a word like her, it would see state 0 and go to 4 because it has an H, and then 7 because it has an E, and it would stop at 8 with an R because there's no more letters in her. What's fancy about this algorithm is the way that it does not restart every time you have failed. If I had HERT and then some more letters after that, this would actually go back to 0, but it would restart again, and it would have to go through each individual match in any other standard algorithm. In ours, what we can actually do, which is very interesting, is if you have like a string such as HSHERS, it will actually go 0 to 1, SH, and then, sorry, SHIS, my apologies. SHIS, it will go down from S to H, and then here it will fail from E, and jump over to the other H match over here to 4, to 5, and 6, and we will still get a rejected state because we will know that that is like a virus match, essentially. What's interesting about this as well is that our accepted and rejected states are probably the opposite of most of how these would work, because we want to reject it if it does reach the end, whereas most will reject it if it does not reach the end. It actually keeps the strings in these states until it has parsed the entire string, made sure that there is no virus where there is a virus, and it will then return this result, and we can actually hide these findings. So how do we hide this? Once again, we've scanned it using the ACDFA, Ahochrastic Deterministic Finite Automaton, but we want to hide it. We want to make this really small proof, the thing that takes 2 milliseconds to verify. And we do that using a zero-knowledge, succinct, non-interactive argument of knowledge. There are 3 important words here. That is zero knowledge and succinct. To start, succinct means very small. Once again, we have a very small proof. Zero knowledge is actually the driving force behind this entire project. With zero knowledge, you can actually hide a fact or a secret that you want to keep and still prove that you know it. For instance, if you were to go to an establishment where they require you to be of a certain age to enter, whether it's 21 for a bar per se, you need to show someone your ID. On your ID, you have your age, you have your eye color, probably your height. There's a number of things on your ID that would reveal to the bartender, that you would reveal to the bartender in showing them your ID. But what if I just want you to know my age? I don't even want you to know my birth date. I just want you to know my age. I would use zero knowledge, and then what that would actually do is it would prove that I am over 21 years of age, but never actually reveal to you my birth date or any of that other information on the page, on the ID. But how does this really work? A very common example has to do with it actually has to do with color blindness. So if I am not colorblind and you have a friend who is colorblind, you can actually test this yourself, and you'll have, say, a red ball and a blue ball. They can't necessarily tell the difference between the two. So what you can do is hand them to them, tell them which one is which, and then look away. They can switch them behind their back a number of times and hand them back to you. And now you tell them which one is which again. If you tell them the right answer, now they can start to believe you. It might take a number of interactions before they genuinely believe you, but they've kept track of how many times they've changed them in their hands, so therefore they can know how you have changed it, or you can know how they have changed it to then derive the secret once again, and they can believe you or not believe you. If you get it wrong once, they immediately know that you're lying. But if you get it right over and over and over again, they can know that you're telling the truth. They can know that you actually know the secret without you ever actually revealing the secret. And in our case, the secret is the malware detection itself. So how do we do this? Now, I said succinct, small. We have a small proof, and with a small proof, that means it's a very, very large backend. So what we actually have to do is split this work across many machines, many computers, from this main node to probably 100 different computers, which will take a bit of these actual arithmetic circuits, because we actually take this ACDFA, the automaton, convert it into an arithmetic circuit, split it across all of these nodes, do all of the work individually, and then come back to the main node to create this proof. This should hypothetically increase speeds by the number of nodes that you have. So if you have 100 nodes, it should be 100 times faster. Using this, it will make it so that we can actually create this proof in a feasible time, and it can actually be a usable application. So where does this leave us? Well, that's the general part of the project. But what did we do this summer? So this summer we finished the automatons. The automaton is completely works. We actually created the encryption algorithm for the email. So when you encrypt the email and lock it away, we have the encryption algorithm working. It formats it into such a way that it actually works with these arithmetic circuits. We take those, send it to our server. Our server does whatever it needs to do with it. We also created a parser, and this parser can take this arithmetic circuit in the format of what's called R1CS. It will take the R1CS, it will convert it from this text file into Java objects. There's a serial version and a distributed version, and this basically means that the serial version is like one computer. If I was just running the entire program on my computer, it will run using this version and a distributed version, which then takes it and uses special objects that allow it to split across those 100 different machines. However, our project is probably 95% in Java programming language right now, but Java is notoriously very slow. It's very useful for a lot of the things we are doing. And a lot of the programs that previously existed were compiled in Java, so that's why we used it in the first place. Java is also an object-oriented language, which means that it's very easy to modify later. So if I wanted to complete this project and add on to it later, it would be much more efficient to use Java than some other languages. However, we found that if we use programming language Rust, everything is significantly faster, to the point where our distributed service alone would be 100 times faster compiled in Rust instead of Java. So we are currently working on a huge design portion of the project. We are trying to design this aspect of compiling most of the project now in Rust instead of Java to create extenuating increased speeds, which will eventually lead to this project's complete success, hopefully by the end of next semester. We've been working on this since January. We plan on continuing to work on this project through this next semester. Hopefully we will have a nice paper to submit by the end of the semester. And so we have got a lot of work to do. We've done a lot of work, and I hope you all enjoyed the presentation. So thank you. And does anyone have any questions about the project? I'm sorry, was there a question? I can't hear anything right now. I can hear mumbles, sorry.
Michael, there were no questions.
Okay.
Okay, thank you very much.
Thank you.
You can use it later.
Good afternoon, Hi, everybody. My name is Kyle Charles. This summer, I spent 5 weeks taking a look at the efficiency of solar cells under Dr. Boreb's mentorship. And towards the end of the project, I looked into the possibility of harvesting waste heat energy from the cells. So as a bit of background, solar cells have been around for over 50 years, and they're basically semiconductor devices that can change sunlight directly into electricity by the photovoltaic effect. However, the very earliest solar cells, they were not very efficient. They had efficiency of about 4%. And so even today, the main focus of research on solar cells is looking for ways to improve the efficiency, the conversion efficiency. So this is just a brief overview of the process of photoconversion. So a solar cell is basically two doped semiconductors sandwiched together, kind of like a diode. You have an N-type layer and a P-type layer. And so what happens is when sunlight falls on the cell surface, then you have the donors and the acceptors from the impurities. They get energized into the conduction band. And so now that they're free to conduct currents, the electric field in the depletion region, which is this red band here, it separates the charges, and that creates a potential difference across the cell. If you have a circuit connected externally, then you observe current. So in this whole process, even though it's a very clean way to produce energy, there are 4 causes for loss of efficiency. And so one of them is the loss of incident light. Solar cells generally are made from silicon, which is very reflective. So if the cell is uncoated, as much as 30% of light can be lost. However, this problem is addressed with anti-reflective coatings and reflective backings. We also have charge carrier recombination, which basically is the free holes and electrons they recombine before they generate current to the circuit. This also has been addressed by having a very thin emitter layer so that the charges are generated very close to or in the PN junction. So as soon as they're created, they can get propelled by that electric field. The cell surface geometry is another area of concern because adding metal contacts to the surface reduces the resistance of the cell overall, but it can also reduce the output photocurrent because there's less exposed surface area. One thing that you can do is optimize the design of the contacts on the surface. Another thing is there's rare contact solar cells that have all the metallization on the back. The final issue with efficiency is that a lot of the solar energy is wasted as heat. As we expect, no conversion system is perfect, so some heat will be generated, but even then, most of the solar radiation is lost as heat. And there's a few different causes for this heat. One, as you can see, is the resistance of the cell. This will dissipate power, which is sensed as heat. Then you have the light itself. Not all wavelengths of light can free electrons because of the band gap of whatever semiconductor material you're using. So wavelengths of light of below this band gap, their energy just gets transferred to the cell as heat. It raises the temperature of the cell. And then finally, even when photons do have sufficient energy to free electrons and holes, they can only create one pair. So that excess energy goes to kinetic energy of the carriers, which creates something called hot carriers. And these give up their energy to the lattice structure of the cell, which is also detected as heat. And this happens very quickly, like under a picosecond. Now, multi-junction solar cells can address this issue. They essentially, you have a lot of different semiconductor materials with different band gaps stacked, and they each absorb the most energetic wavelength of light. But this typically is an expensive solution. Hot carrier cells are also proposed, but they have yet to be completely realized. So one of the questions that stuck with me was if there's a way to harvest this heat and somehow convert it back to usable electricity. So as you can see, I have a little graph here of the irradiance or the amount of sunlight versus power output. And what it's illustrating is that even though the waste energy reduces efficiency because of course that's output that you don't collect, but a higher temperature also reduces the efficiency of the cell. So it's something very important to try to address. And so these two fields, they're actually based on performance of Canadian type solar panel, a model of which was available. Previous studies have shown that solar panels work best if they're kept at lower operating temperatures. And so some solar panel users have tried to make their own cooling systems. So you have integrated water heating systems whereby the heat from the solar panel can be repurposed to heat water or drive steam engines. But typically, cooling systems don't make good use of this energy. So I looked into pyroelectric materials, and these would be ideal because they can convert changes in temperature to a temporary voltage. If heating and cooling occur rapidly, then you can draw a lot of power from them, even though the difference in temperature is small. So like the ideal temperature versus the actual operating temperature of this panel, even if that's not a very big gap, you can still harvest a lot of energy. So the challenge with this though is that you have to achieve a time varying temperature without adding a lot of work because there are no moving parts or vibrations associated with solar panels. So heat sinks would be a good option for cooling because they don't require any input power. And so I looked at pulsating heat pipes because they're do have a working fluid which oscillates between a heater and a condenser through adiabatic section. And so here you have a visual of what a pulsating heat pipe looks like. This section here in red is the heater, where vapor would be generated in the working fluid. Then you have a cooling section on top, where that vapor cools and condenses. And in between you have just this adiabatic section, so that the working fluid can move between the two sections, so that it keeps heating and cooling in a cycle. So this is one possible approach to using a pulsating heat pipe for cooling. The solar panel would provide the heat for the heating section, and then you could have the condenser and the adiabatic section extending upward or out to the side, and so the air can cool the working fluid. So this is a simulation that I did in the student version of ANSYS, just to observe the pulsating motion from the heat pipe. So the very dark blue section, there's no water, and the different colors tell you what specific volume of water is available. So like a lot of water wherever you see red. Let's see. One second. Yeah, so I know it's kind of hard to see because of the colors, but over time, as the fluid heats up, it does begin to move through the pipe. It also changes to steam, which is why you have the graphic becoming very light blue. There's another simulation just to show the variation of temperature that happens on the walls of the adiabatic section, which is really the useful part of this whole setup. Probably that's the same thing. I'm almost done. So yeah, there's a lot of different parameters to play with and to try to maximize. But even without that, I did see a variation in the surface temperature. I picked one specific point just to look at the temperature over time, and this shows you how it changed. So we do have a time varying temperature that we can harvest energy from. This is a model of an equivalent model of the pyroelectric being used. So current, this is the formula for the current, and because it's also a charge storing element, there's some capacitance and a real resistance associated with it. So I used MATLAB to help me program what the output voltage would look like. And so this is the signal that I observed. Yeah, so just really quickly, areas I would have liked to improve on, as I didn't know too much about the heat pipes or even the pyroelectric material. So to improve the design, I would have to learn more about them, including strengths and weaknesses and how to set the parameters. Some of the assumptions I made, which my design would not hold true over a long period of time, like the panel and the environment will not always be at a constant temperature. And I only looked at pyroelectrics at one point on the pipe, but I'm sure by adding elements at various points, we'll be able to harvest more energy. I just want to acknowledge Dr. Gloria for his mentorship and the benefactors who have made that final possible. And these are some of my
I'm Nick Vine. I'm a rising junior mechanical engineering major, and my advisor was Dr. Booty. And we ended up using MATLAB App Designer to make a schedule maker. So basically what we were trying to do was make freshman engineering students, and obviously beyond too, allowed to have something that will make their lives easier when they're trying to make schedules. I know personally when I was a freshman, making a schedule was very daunting. It was like something that I was not really sure how to do. So that's why this was something that we thought would be very beneficial for students to have. So the steps that I took were first doing some background research on how actually App Designer works, and then, which is basically just a modern version of GUI, if any of you guys have used that from MATLAB. And then I always had to plan out, and so basically we would either draw out or we would just discuss in words what we would want to do, like how we would want the app set up, and we would obviously have to code it and then just continuously repeat those steps. So let's check out the 1.0 version of that. And this is where I drew it out, and this is what I sent Dr. when we were trying to think if this was good. I don't have the actual screenshot of the first version of this code, but this is what it basically looked like just on paper. And we basically required students to make an Excel sheet for their transcript, and then from there it would have been able to propose a schedule. And this version really did not work too well because it ended up just forcing a lot more work out of students, almost more work than making a schedule on their own. So then that's what led to Schedule Maker 2.0, where we ended up having buttons up here for transfer credit, and then where you can type in directly here, and then there's just buttons. There's a lot more buttons, but that's the difference. The main difference from the first version to this version except it's still a lot of typing that's involved. And so the next goal was kind of to just have everything be strictly buttons, and so it's not as much of a tedious process to go along. And also, the app wasn't very user friendly to look at. It's very like pieced together, so we wanted it to be a lot more fluent when looking at it. So that's what led us to ScheduleMaker 2.5 version, because now I have it a lot more organized. You have your major first. There's some now messages that pop up, and based on what major you select, different things are enabled and disabled. Like since I had mechanical engineering enabled, there's not a BS elective, and you don't have to take psychology and sociology. So, and these obviously you don't have to take a mechanical engineering major. Still, though, it wasn't the best version of this app. So the reason why it didn't really work was because you still had to do a lot of clicking in order to finally add everything in to the app, and it really was still not the most user friendly, because it still was really two like pieces kind of. So we wanted it to be one vertical like viewing. So that's what led into the final version, which is ScheduleMaker 3.0, which is this, which is, it can look like a big jumbled mess right now, but I will show all the different features. So now users are able to save their data, they're able to load data, things appear and disappear, and basically now with this version of the app, users are able to go down 3 different paths, and the 3 different paths are, if the student has transfer credits, they go down path 1. If they don't have transfer credits, they go down path 2. And then if they've already used the app before, they go down path 3 to load their data. So we check out how path 1 looks. This is how the screen looks when it would first look after you click yes. So just imagine this which is how the app would look in general. But then once you click yes, this whole section pops up. Then after you select what you would come in with, you click process transfer credits, and it would add it to this table and it would show you that it says status TR. And then after that, it would also disappear in this table right here. So now with this version of the app, you're able to add them all at once into this table, where it shows your current schedule after pressing process and progress class. And then after that, you would add it to your transcript, and then you click save data, and then a message would pop up saying transcript saved. And then from there, you would generate your proposed schedule, and then after clicking which semester you would want, spring or fall, and that all affects what's here, which is your available courses. And here's like a proposed schedule that did come up for what this would be freshman spring semester, and this would just be something that would be proposed. And what users can always do is if you clicked on this, it would bring it over here, and then vice versa, click on something over here, it would bring it to this table. So it's fully editable for users too. It allows them to completely see what they can take, and then what they're also forced, like what a proposed schedule would look like. So then from there, they would type in like what they would want to save it as, and then once they click save, it would say schedule saved. And then if they wanted to even save another one, once you edit this, that message would disappear, and then you would just resave it as something different. So now, if you go down path 2, the only difference is that now there's not a section for transfer credits. If you click now, it just brings you right to the next part. Now, if you look down path 3, this is a different one where you now click load data, and that brings you right back to your transcript that you had previously saved. And now this new message pops up where it's delete any course that you did not pass, and the only thing you have to do to delete the course is you click on it. But then if you did pass those courses, which is how I set it up here, if I did, I click change IP to P, which is in progress to pass, and then it changes all the in progress classes that I had previously added to pass. And now another new feature right here is where you would type in like your old file name for what you had previously saved your schedule down here in. So then after doing that, it pops up over here. Again, you can edit it. Then if you ended up changing your schedule that you had, let's just say, oh, I didn't want Chem 3A anymore, I want a different class, you would just click it out and then add process and progress class, and then finally add the transcript and save data. So that's finally. After that, you would generate your proposed schedule again, and then it would just bring you right back. So that is all. Thank you. Yes. Mechanical engineering. May 2024. Okay. Okay. I thought it was tedious to some extent, but I didn't think that I thought that it definitely worked well for what the purpose was. Especially like App Designer, like I thought that it had a lot of good features, and I thought that App Designer was a lot easier to use than GUI. In GUI, you had to use like handles and stuff like and get and set features. This was a lot of just like set like usually just put equals for it, so it was a lot easier to code with App Designer than it was. No, but after like me and Doc did a lot of like just runs between ourselves, like we would just try this through different students, and we just that's how we ended up coming up with ways to fix it. Because when we were just running it as if we were other types of students, like industrial engineering, whatever other kind of majors, that's how we would come up with new ways to fix and add different things to the app. It does account for prereq courses already. It does not account for time conflicts because I wasn't able to figure out a way to get information from a server. But that was definitely something that like me and Doc had talked about. Is something we wanted to, if I had more time to work on it, something that I would have wanted to do. Computer, yeah. Yeah. Any other questions? Thank you.
Hello, everyone. My name is Jason Chung, and today I'll be presenting my research topic that I did with Professor Alexander Rosenberg, which was the exploration and application of IoT tools in MQTT. So to start off, what is IoT? IoT is otherwise known as the Internet of Things, which is a network of devices embedded with sensors, softwares, and other forms of technologies for the purpose of connecting and exchanging data with other devices or systems through the internet. From here, you may ask, why should we care about IoT? Well, the reason as to why we should care about IoT is because it is literally one of the most important technologies used today. Almost everything that we use, for instance, such as our cars, our refrigerators, or even our thermostats, can connect to the internet due to IoT to allow seamless communications between processes, people, and things. Not only that, IoT also provides many benefits, such as the ability to track and monitor things, help decrease workloads by using automation, and it can also help increase efficiency by saving money and resources. So now knowing why we should care about IoT and its importance, we can now move on to how it works. So IoT works by using a concept called IoT protocol, which is an integral part of IoT technology stacks. The reason for this is because IoT protocols and standards is what allows hardware to have the ability to exchange data to begin with. So given that, IoT protocol can also be broken down into two classifications. The first classification is IoT data protocol, otherwise known as the front-end component or the application or presentation layer. Some examples of IoT data protocols are HTTP, WebSockets, and MQTT. The second protocol classification is IoT network protocol, which is the back-end component, otherwise known as the data link or physical layer. Examples of these are Wi-Fi, Bluetooth, and Threads. So now knowing what IoT is and the general concept of how it works, we can now transition to MQTT, which was a IoT data protocol example that I mentioned on the previous slides. Basically, MQTT is a OASIS messaging standard protocol for IoT, and that it is designed to be a lightweight messaging transport, ideally for connecting remote devices with small code footprints and minimal network bandwidth. So nowadays, MQTTs are now being used in varieties of industries such as automotive, manufacturing, and consumer products due to the many benefits that it provides to their workflow. So given that, we can now move on to how MQTT works. MQTT works basically by using a concept called a central broker, which is a central core component for MQTT infrastructure system, and a publish and subscribe model. So basically how this works is when a client publishes a message to a topic, our broker would then distribute that message to any connected client subscribed to that topic. Once the broker has distributed those messages to any connected clients that are subscribed, the message is then removed from the broker. However, if there are no connected clients at the time connected to that subscribed topic, the message is then immediately removed from the broker. So now knowing what IoT and MQTT is, we can now enter the main part of our project. So using the concept of IoT and MQTT, we wanted to explore IoT tools and technologies for possible integration into robotics project. Specifically, we wanted to investigate methods using a ESP8266 or a ESP32 board and MQTT for remote sensing and remote control application to improve navigational purpose on the deep dark paw robot as shown on the left. So before I explain why we wanted to improve the navigational purposes on the deep dark paw, we must first know what a ESP8266 or a ESP32 board is. What a ESP8266 or a ESP32 board is basically a microcontroller that are single integrated circuits that could gather inputs and output a certain behavior based on the information gathered. So now knowing why, the reason why we wanted to improve the navigational purposes on the deep dark paw was because last summer we created an autonomous robot using it that was able to track and follow a line using machine learning and AI libraries, such as OpenCV and NumPy. However, although we were successful on doing it, we did face some minor issues, such as limited field vision and external factors such as lighting, image quality, and noises. So in order to resolve these flaws, we wanted to use IoT and MQTT. So in order to do this, we first explored various sensors and created programs for each individual sensors to be able to work and communicate with MQTT. So some sensors that we used were a relay, a PIR sensor, a IR sensor, a ultrasound, and an ARDUCAM. Once we were able to create a program for each individual sensor to be able to communicate and work with MQTT, we will then merge all of these sensors under one program to be able to connect and exchange data with one another and concurrently in order to achieve task management. So while doing these, we also face some challenges and limitations while doing the workaround. So starting with the limitation, the first one that we faced was that not all sensors are created equal. So what I mean by this is that there was a fairly substantial difference between the reliability and accuracies of each sensor despite being the same general price range. The second limitation was the sensor capability itself. So the first one was a PIR sensor, which had huge delay time, even when set to the absolute minimum, and that it was constantly recalibrating every second. Another example was the IR distance sensor, and the problem with that was that it had very limited range. And lastly, for the ultrasonic sensor, the problem with that was that it would always constantly provide inaccurate reading if an object was too close or too far from it. So now for the challenge, the biggest challenge that we had to face was the single thread limitation of the ASPiRE board in order to perform multitasking. For example, when we tried to send commands to the board and trying to get video streamed back concurrently, it would cause issues due to the large code footprint. So having these challenges and limitations in mind, we decided to do something simpler, which was creating a motion detection for a door. Basically, the purpose for this is to imitate healthcare assistant robots that could immediately aid people when a door is open. How it works basically is when the door is open, our MQTT will then send a message to any designated client to perform a specific action and vice versa when the door is closed. So by performing these applications, these are the goals that we've set in mind. The first goal was being able to access each sensor capabilities. The second one was to improve navigational capabilities by using constant data feedbacks. The third one was the ability to react to events and environmental conditions. And the fourth one was the ability to toggle a relay based off of sensor reading. So basically with that, this was the following setup to do the motion detection. As you can see, we had one ESP8266 board that was connected to an OLED and a IR sensor. We also had another ESP8266 connected to a power relay, and then we also have the robot itself. Basically how this works is we will have the ESP8266 board with the IR distance sensor and the OLED to be placed perpendicular to the door in order to see if it's open or not based on a certain data range. When the data range is met, the IR sensor would then publish several messages to the broker to turn on the relay, which will activate a light and will tell the robot itself to move. And once the IR sensor detects that the door has closed after being open, it will publish several other messages to stop what it's doing. The video doesn't work, but basically it's just when the door is open, you would then see the relay being turned on, which would turn on a light switch, and you will also see that the robot will move itself as well. So Although we were successful, one of the main issues was the time delay of the deep dark pod itself, was because due to how big our code footprint was, it would cause the robot itself to have difficulties immediately shutting down by itself. But regardless, everything else worked. So having that, our future goals for this project is basically the following. We want to have the ability to access the sensor itself that's built into the robot rather than buying external sensors and just building on top of it. The second goal is implementing triggers based off of an event. The third one is being able to use voice control. So basically like an Alexa. So like when we say, hey Alexa, Alexa will turn on. We want to do something similar for the robot itself. And once we're able to do that, we want to be able to control a variety of robots, even with their from different companies under one app, which we can control all of them. Pretty much it.
Currently, we're wanting to use a LiDAR sensor, which is basically a sensor used by the ground to measure how far, how far something is using light. Yeah.
Hey Gianna, can you hear me?
Yeah.
Okay, so I think in 5 minutes you're going to present, so at 2:40.
Okay.
So I guess if you want, you could go ahead and share your screen, your slides now. We'll just make sure that it works.
Yeah.
Yeah, okay.
Okay.
Everything looks good. I'll let you know when everyone's back and when we're ready to start.
Okay. Thank you.
Yep. Hey, can you hear me, Gianna?
Yeah.
All right, so we're gonna go ahead and get started, everyone. So this summer I had 3 students who I worked with for 5 weeks each for ASPiRe, and Gianna will be the first of those students to present. So they all worked on a overarching related project, so there's gonna be some things that overlap, but they generally worked independently for 5 weeks each and are gonna present on what they worked on mostly. So Gianna, you can go ahead.
Hello, my name is Gianna Rinaldi, and my summer ASPiRe project was working with plant-based scaffolds and assessing their mechanical properties as well as their interactions with cells. I worked on this project under the mentorship of Dr. Myrna, and throughout the summer I mechanically assessed the leaves with various techniques and paired them with cells to see how they interacted. So a little bit of background about coronary artery disease. It's actually the leading cause of death in the US with over 610,000 deaths annually. And this disease occurs when there's a large amount of plaque that tends to build up in the coronary artery, causing it to become blocked, which leads to the lack of blood flow to the heart and can eventually result in a heart attack or even death if not caught in time. There are over 3 million cases in the US each year. Vascular grafts can be used to replace the artery. However, the gold standard is the autologous saphenous vein. This can be taken from a patient's leg. However, they aren't always readily available and oftentimes may be damaged. This was the motivation for exploring the possibility of using plant tissues as vascular grafts. This project began with using black-eyed Susan leaves as the main source for the grafts. Throughout experimentation with various detergents and enzymes such as trypsin, turgitol, EGTA, and STS, a decellularization protocol for black-eyed Susan leaves was developed. These detergents and enzymes are used to wash away the native cells and DNA, leaving behind a bed of proteins called the ECM, or also known as the extracellular matrix. This technique allows for the plant leaf to keep its strong structure while making it available for new cells to inhabit without negative interactions. The goal of this project was to use the resulting leaf scaffold after decellularization and to take it and roll it into a tubular structure to resemble an artery. We first had to figure out what binding agents that we had to use to keep the leaf rolled, as cell-to-cell interactions are not strong enough. After reading a paper from Nara Medical University about gelatin glue for rats, we decided to use gelatin and glutaraldehyde as our glue for leaf strength and solubility. After extensive testing and rolling the leaves with different gelatin and glutaraldehyde concentrations, it was found that 30, 40, and 50% gelatin worked the best based on hardening times as well as consistency. Glutaraldehyde at a 25% concentration was optimal. After obtaining these results, some standard tests had begun. Cytotoxicity testing was performed to observe the behavior of cells while in contact with gelatin and glutaraldehyde. This was to make sure that after a certain period of time, there was still a viable cell population. Optimal gelatin and glutaraldehyde concentrations were placed in each well of a 24-well plate, and each well was seeded with 50,000 cells. At the end, they were observed over 6 days, and at the end of each day, we got to observe them under the microscope. After a full 6 days, a viable cell population seemed to remain as pictured, indicating that this experiment had been successful and that the cytotoxicity test was passed. It was now time to repeat this experiment with the leaves, with the 2D sheets. Half of the leaves had a separate gelatin, glutaraldehyde, and separate layer of cells used, and this was the monolayer samples. However, the alternate leaves had gelatin, glutaraldehyde, and cells all mixed together and then placed on the leaf to resemble a 3D seating environment. Since the green-colored leaves unfortunately prevented imaging with a cell culture microscope, the experiment was only able to be imaged after the final day, that being day 6. The sheets were stained with DAPI so that cell nuclei could be observed. We were able to use a fluorescence microscope to image, but as you can see, only few cells could be seen. In the future, we plan to use a different DAPI staining protocol, which will be used to obtain clearer images, allowing us to count the cells with a computer software called ImageJ. The next experiment was done to test the solubility of the leaves. This was done to see how the 3D rolled scaffolds held together in media after a long period of time. It was an important long-term goal. The long-term goal is to implant scaffolds into an animal model, so we must ensure that the vessels are stable over a long period of time. The leaves were rolled around an acrylic rod using gelatin and glutaraldehyde as the binding agents as discussed previously. They were then placed in small 15 milliliter conicals and submerged into the media. This test was run over 5 months, and the final results were recorded during my final week of ASPiRe. The 30 and 25% glutaraldehyde intact leaves came off the rod nicely, but they were swollen and puffy. The intact 40% gelatin with 25% glutaraldehyde leaf came off the rod without unraveling. These were promising results which enabled me to perform burst pressure testing on the rolled up scaffolds. The heart, which is attached to the coronary artery, acts as a pump, creating pressures of 80 to 120 millimeters of mercury, or 2.3 psi, to be placed on the artery. In order to simulate these forces and ensure that the graft would maintain its mechanical integrity, after implantation, burst pressure testing had been performed. This was done with the solubility tested leaves, the intact leaves, rolled leaves with superglue, as well as decellularized leaves. The rolled leaves had MPT barb fittings inserted into each end and secured in place with superglue and parafilm. At one end, the barb was connected to a pressure gauge via tubing, and at the other end, it had a water-filled syringe connected to it. One person held the 2 ends of the tubing as the other squeezed water through the syringe. Once the leaf had bursted, the pressures were recorded, and most of the leaves exceeded or achieved the standard pressure of 2.3 psi. The 30 and 40% gelatin leaves from solubility testing had PSIs of 7 and 5.8 respectively. In the middle of the summer, we ran into a big issue with the black-eyed Susan leaves. These leaves come fresh from the garden, and for some reason were breaking and disintegrating in the middle of the decellularization process. This was the first time we had used these leaves since the last summer, as they are only in season during the late spring and summer months. Overall, we had inconsistent results, and there were periods of time where the leaves had prior performed well based on seasonal differences. Some protocols had varied from good to bad. We had suspected that this could have been due to the temperature of the shaker or the climate that we were in. In an effort to rule out multiple factors as to why these black-eyed Susan leaves were disintegrating, we picked a bunch of them from different plants and began testing. A control group we used was placing intact black-eyed Susan leaves in regular deionized water. We used both the shaker and the rocker for this. This was to see if the shaker we had been using had been causing the issues all along. We decided to put multiple black-eyed Susan leaves with the same conditions both on the shaker and rocker. Ultimately, these deteriorated and led to the decision to no longer use these plants. Not only were they breaking apart, but we also felt this was appropriate as they were only in bloom for 1 season, meaning that they are not readily available. So in lieu of using black-eyed Susan leaves, we decided to use a new leaf called leatherleaf viburnum. We had briefly tested these alongside the black-eyed Susan leaves. We found these leaves to be good candidates as they rarely break and are more robust than the black-eyed Susan leaves. and there's abundance of them as we can get them from school. In fact, they are readily available throughout all seasons. From now on, we will be exclusively experimenting with leather leaf viburnum leaves for vascular scaffolds. In conclusion, various mechanical and cell tests were performed on the leaves. The leaves were successfully rolled with lab-made glue to create 3D scaffolds. Now we have optimal decellularization protocols, as well as the type of leaf that we want to continue the project with. Future plans include seeding these cells onto the 3D scaffolds and coming up with protocols to image and count them. I was only able to participate in the 5-week ASPiRe program. However, my colleagues took the project further in their succeeding weeks. With that being said, this is the end of my presentation. However, my colleagues were able to accomplish more throughout their time in the lab. Thank you so much for listening to my presentation. If someone's asking a question, I can't hear.
Hi, Gianna. Any questions? Gianna?
Yeah, I'm here.
Looks like you have a lot of challenges with microscopy. So how do you anticipate to be able to successfully show that you're able to carpet your leaves with endothelial cells?
We're gonna try different DAPI concentrations, and we might also try a different stain altogether to see if that gives us better luck. But we also have to put more research into how to stain the plant leaves properly.
Because also the API requires you to kill the cells, right? You fix them.
Yeah.
So
with formaldehyde.
You may want to keep them live and use something like Hoch or do BRDU assay to check viability.
Okay.
So I think fixing them and killing them and assessing them may not be the right way to do it. Just a suggestion.
Okay. Thank you.
This is Eddie Curry. I was just wondering, once you get the skeletal structure populating with cells, does the skeletal structure remain?
Yeah, so what's left is like the leaf without the cells and DNA. And yeah, the structure still remains strong because we tested protocols last summer as to how to take the cells off and the DNA without interrupting the actual mechanical properties of it. And we made sure of this by mechanical testing, as my two other colleagues will say in their presentations, and also by the burst pressure testing that I mentioned. So we ensured that the mechanical properties were still okay.
Okay, but I understood that this was an alternative long-term of replacing using leg veins. If that's true, you end up with a cellular structure as part of the skeleton structure. Does the skeleton structure stay there indefinitely?
We tested it for 5 months, just in media. There were no cells yet. We plan to do that in the future, but in the 5 months that it was in the media, the leaf stayed intact and the skeletal structure still remained.
Okay, thank you.
Next, we have Nicole coming up.
Okay, hi, my name is Nicole Grabenko, and my project focused on decellularizing leather leaf for vascular applications under Dr. Nicholas's Myrna mentorship. And this tree right here is actually the tree that we use in Hofstra campus, just to have like a reference idea of what the leaf looks like. So as previously mentioned, the coronary artery disease is the leading cause of death in the United States. So our approach to resolve this was to make a vascular graft based off of leaves. And as previously mentioned, also black-eyed Susans were the leaves that we used previously, but they did disintegrate. So we had to pick out a few leaves from Hofstra campus and just see which one would be the most successful. So after testing, we tested like a waxy kind of leaf, a fuzzy leaf, which was leather leaf, and then just a regular one. And we did see that the leather leaf had the highest elastic modulus as well as the highest DNA removal after decellularization. So I'm going to continue talking about assessing the mechanical properties as well as different decellularization techniques. And like I mentioned, leather leaf has a much higher elastic modulus, and the DNA removal was nearly very close to 100%, which is why we call it to be successful at the moment. So going into decellularization, it is the process of removing any foreign DNA that is left on the leaf. And that is the goal, because if we implant a leaf that has not been decellularized, it will cause adverse reactions such as immune response, infections, or even rejections. So now, in order to decellularize, we had to try out many conditions in order to get the good one. And in order for decellularization to be good, we assessed as to how much DNA it removed. And not only as to how much DNA it removed, but actually as to how high the elastic modulus was, as well, which intends that the mechanical integrity is very strong. So the best results that we got was a DNA removal percentage of 95.5%, and the elastic modulus was 3.114 newtons per millimeter squared. And we did get higher DNA removal percentages, but this one had both a very high DNA removal and a high elastic modulus. And the condition for that one was sodium dimethyl sulfate and EGTA. It was a 4-day process where they were interchanged, and then 6 hours of clearing, which I'll get into. But just the 3D model on top is showing you what shape that we use for decellularization, just to keep all these sizes and shapes consistent throughout. And this just led us to have less error throughout our experiments. So now going to clearing solution. Sorry about the picture being a little blurry, it's just how it went through the slides. But clearing solution is a very important step in decellularization, because we did notice that if we don't use clearing solution, the DNA is still left on the leaf, which I'll show a few pictures of, but that means that it did not fully decellularize, and that became a problem for us. So the reason that it's not complete decellularization without clearing solution is because DNA removal requires there to be both anionic and non-ionic detergents. So the clearing solution that we made, that we were using, was based on a previous literature review that had spinach as their leaf for different uses. The clearing solution was made up of 100 milliliters of deionized water, 100 microliters of Trident X100, and 10 milliliters of bleach. So we wanted a 0.1% of Trident X100 because it is a very strong chemical. So also while we were using clearing solution, we wanted to test a few different time standpoints. We tested 3 hours, 6 hours, 12 hours, and 24 hours. For 3 hours, as you can look at the top, it did not clear our leaf at all. It left a lot of brown specks across of it, so therefore DNA has not been removed. 6 hours were actually our chosen time point because it had the highest elastic modulus of 1.31. However, 12 hours, we already saw a decline of elastic modulus where it went down to 0.768. And and 24 hours, we weren't able to test because it ended up falling apart. Therefore, we knew 24 hours would not be a working time point for us. So now going into just a few examples, the picture all the way to the left is a few different conditions of how the leaf starts off. That's just a leaf going to the rectangular shape. Then the second picture for each of the conditions shows about day 4 for the first two, and then day 3, because SDS only is 3 days, and then EGTA and turgitol and STS turgitol are 4 days long. And then the final picture is showing you after clearing solution for 6 hours how the difference is. So if you look at the middle picture, that's without clearing completely, and you can see that it still has its color fully, therefore it still has DNA. And then after we use the clearing solution, it has no more color left over, which let us know that the DNA was almost fully removed. So now going into tensile testing, also known as mechanical testing. We were using a machine in the materials lab through a Blue Hill program, and I decided to make this 3D model where we cut each of our D cell conditions into this dog bone shape. And the reason we did this is because of the curves being very essential as to how the forces are distributed along the leaf when it's being pulled. So the leaf would be clamped on the edges, and then when the leaf was being pulled, it would rip essentially in the center if there was no error seen. And I'll show a graph of example, but that will let us understand what the highest extension is as well where the breaking point is. Before this, we ended up using an I shape. It had no curves on it, and we did notice that it was actually ripping at the bottom and top and not in the center. So we had to adjust our model to have the curves because of this reason as well. So here's just an example of like 4 of our samples that we had. This is the graph that we got from Blue Hill. The blue line is just showing like the highest point, the ultimate strength, where we got a force is about like 1.52. And based on this and the extension that you see, if you drop that blue line down, it's like 2.75. We would use elastic modulus, which is stress over strain. So the forces from the graph, the dl over L is also the change in extension. And then area we would calculate based on this middle section of where it's being pulled. So we would go a little bit under the curves, and that would be your area. So for the final experiment that we did, it was burst pressure. And as Gianna previously mentioned, burst pressure in the coronary artery is 80 to 120 millimeters of mercury. And this is very important for us because if we implant our graft just without testing burst pressure, it could fail on us and just rupture completely in the vessel. And then the process is going to restart and the person will not be helped in any way. So the setup of how burst pressure looks is just right here in the right picture. We have a syringe of water with our little graft, and that is in the tubular shape, and then it has all the fittings to the pressure sensor. So you would push the syringe of water, and then essentially it would pop in the middle, and that's your pressure for the burst pressure. And the bar graph over here is just showing a few examples of what kind of results we got. The intact 60% was just a leaf without decellularization. That was roughly 60% gelatin and 25% glutaraldehyde, which is about 870 millimeters of mercury, which was very high. And then as D-cell, our most successful one was about almost 700 millimeters of mercury. And that was decellularization with 50% 50% gelatin and 25% glutaraldehyde. So overall, our D-cell conditions would be successful if they were implanted just based on burst pressure results at the moment. So just some more burst pressure. We had some complications because the leads weren't popping in the correct area when we were testing them. So we thought that maybe the wetness/dryness affect the leaves. So we did a few experiments by pat drying them 1 time, pat drying them 3 times, and then pat drying it until it's almost fully dry without dehydration. And we left one completely wet because after decellularization, we do store it in deionized water. So when we did notice the more dry it is, the less likely it will hold the gelatin. The bond just became very, very weak. So we just stuck with the way we usually did it of keeping the D-cell just completely wet and just rolling it the way it was. And we also assessed different gelatin percentages. We went up to 60% this time. We did 40%, 50%, and 60%. The higher gelatin you go, the better the leaves rolled and the bonding was a lot better. But 60% is very hard to handle because it does solidify quickly, so we had to optimize our protocol for that. But 50% did seem to have very high burst pressure, so I think we might pick a range between 50 and 60 and test those out a few times. And yeah, just in conclusion, we saw that all of our results made the leather leaf would be successful in becoming a scaffold. And our future experiment would be to repeat these experiments that I mentioned to get some NF2s and NF3s, just to make sure our results are consistent. And also we would like to eventually recellularize these grafts by seeding cells onto them. And we did a few other experiments, but my other colleague will take over that by explaining those as well. Well, so I'm thinking that, I'm thinking it's because of the gelatin. So the native vessels they are pretty strong, but our gelatin does make our grafts a lot stronger because of the bondage. We're using pretty high percents. So having that gelatin within our graft just makes the bondage within it a lot stronger and means that it will burst only. Yeah. For which one? It was in the beginning, right? That was without gelatin. We're not able to test the mechanical strength with the gelatin. We have not done that yet. Yeah, I think it was 3.11. No, it wasn't that one. Our highest elastic module for impact was about 3.65 newtons per millimeter squared. No, what do you mean? For the intact burst pressure? Yeah. Yeah. I have not looked into that, but I know that the coronary artery burst pressure is nearly 80 to 120. Its elastic modulus is very low though. For the native vessel, it's around 0.08 newtons per millimeter square. So I don't remember the number specifically. I know I've looked into it before, but I don't remember the number off the top of my head. We have not measured the density.
that we
without using notes, articulating what we've done. Most of them done, research is not an easy thing to do. That's why you don't always work before research, because you have to repeat the search, same search several times, looking at some of these things that you see some answers. And really want to encourage the students to participate in this project, to succeed in doing that thing if possible. And because it would be wonderful if you're able,
Check, check, check 1 2, check 1 2. Check 1 2, check 1 2. Check 1 2, check 1 2. Check, check, check 1 2. Check, check, check 1 2. I didn't X anything out. I just went in to check the audience.
Okay. Okay. Okay, take care.